Okay, we are now recording. Let's get the slide set up from current slide. And let me make the last few announcements, okay? Again, I wish I had waited to say the other. Okay, we are going, knock on wood, are going to finish chapter 23 today, okay? As soon as we get 23 finished, we'll go on and start on 24, last chapter we're going to do. Then, 30 minutes before the end, that'll be around 4:30-ish, we'll pause then, and you can take your test on chapter 20, which we finished last Thursday. Okay? So, now, here's where things sit for the lab. I called channel 13. I never can get Jerry Tracy in person, or very rarely. But I did call and talk with. They had someone answering the phone this time. Sometimes you just leave messages, they never get back to you, or you know, if I'm not in the office, I don't hear it when they get back. But I did get somebody on the phone. She connected me with someone in the newsroom. They connected me with Harmony Mendoza, not Jerry Tracy, but Jerry wasn't there yet. And she said she would initiate an email getting the word to everybody, and hopefully I'll hear back from Jerry. Now here's the deal. Most of the time he doesn't come in because he works until like 11 o'clock at night. He doesn't come in until around 2 o'clock in the afternoon. So she said that she thought his best time would be 2 to 3 or 3 to 4. You got to get it done before the news starts that day. So some time like that is probably the time he's going to have to host us. So that's why I was saying it's going to be right in the middle of the day. But if that's more convenient for you, I'll be recording everything on Screencast-O-Matic, and it'll be on YouTube. So you can handle that if you want to, and you'll be counted present because you'll be there at the thing. Now, what's that? Okay, that's the thing. We don't know yet because he hasn't gotten back to me, but I gave them the dates. I said we either need it Thursday, Tuesday, or Thursday of next week, because I believe Thursday of next week is technically our final exam day. Is that right? Has anyone checked that? I believe we have class on Tuesday and finals on Thursday. So, but if they can't get us in this Thursday or next Tuesday, we can do it that last day, and we'll still have plenty of, yeah.
You said you had the final exams on Thursday. Are those going to be at the beginning of class or at the end?
Typically, it's all we do that day. Okay, but if we are going to channel 13, then we'll do it as channel 13, and then it'll be after we finish channel 13. So, but usually that's it. And also, let me say this, and I'm glad you sort of asked that question because it prompted me for something else I need to say. I want to have returned to you all your labs and all your tests by next Tuesday, 1 week from today, which means that I need them all in and completed before next Tuesday, okay? So please try to get these things. One person came in and made up 2 tests today. I've had some labs and other things turned in today. So please get your stuff in. If you're deficient in anything, please get that to me sooner rather than later, because I want to return everything. As soon as I get everything in, I'm going to return it then. But if I don't have everything in, it's going to go back next Tuesday. Whether it's yours is in or not, that just gives you a 0 for that input. So please don't get a 0, do your stuff. Okay, and if you'll check on Blackboard, if you're missing a score there, okay, I think that's my phone again. Let me see if they're calling back. No, it must not have been my phone. Okay, so anyway, if you don't have something done by next Tuesday, it's going to be a 0. So please try to get it in, or portion. Oh, though I was saying, you can check on Blackboard, and if there's a blank there, and it's not something you've just turned in today, then I don't have it. Okay, so you can check. That includes your papers. Let me, in fact, go over that since we are close enough to the end. And let's see, did I get everybody? Yeah, I think I got everyone coming in. Okay. I've only received 5 papers out of 15 students. So 10 people haven't turned in papers. Lab 1, I've still got 2 people who haven't turned in Lab 1. One person hasn't turned in Test 1, but she did it today. So I can return your Test 1 to you right now, and that's Bianca, right? Okay, let me get Bianca marked present before I do that. And I can now return your Test 1 because the last person took it today. Okay. All right. Here we go, jackets. Okay. Of course, very few people are here to get it, but I will still return it to those who are here. Brendan? Oh, Brianna's not here yet. Galen is no longer with us. Darius is not here yet. Emmanuel? That's one. Today, the last person, that's one. Tyra? Laundry or Coco's not here yet. Bianca is. James is. Josh is. Roll now. Okay. Carrie's not. Carl's not. Shelby is. Brittany's not. And Terry's not. Okay. So, not too many I could return, but it's all that are here. All right. All right. Continuing. There's Test 1 has been returned to everyone who is here. Lab 2, still missing 2 labs. Test 2, still missing 1. And she took it today, so I can return Test 2 to you now too. So let me get this done. Test 2. Okay. Brendan? Deanna's not here. Galen's no longer here. Darius is not here. Emmanuel is. Tara is. Up here. Coco's not here. Bianca is. James is. Josh is. Terry's not. Carl's not. Shelby is. Brittany and Terry are not. Yeah. Okay. So I've returned Test 2 to all who are here. All right. Lab 3, I've received 1. That's the Moon Lab, 1 Lab 3 in. Okay? Y'all need to be wrapping those up because the moon's going out of sight now, I think, yes?
If we went to that, the Sanford thing,
Yeah.
Does that replace the library?
Yeah, you can use that to replace 1. Yeah.
Okay.
Okay. Test 3, I've returned that to everybody. Hopefully everyone here has gotten it. Lab 4, which was the field trip to Sanford. If you were there, you got 25. If you weren't, you didn't. Okay. Lab 5, which was the next lab that was on properties of minerals. I've got 2 people still haven't done that one. Test 4 on that chapter, 3 people haven't done. Lab 6, which was the one with the questions, I got a few in today, but bunches of people haven't done that. I only see 1, 2, 3, 4, 5 of those, and I think I got 1 more today. Okay? Test 6, missing 1, 2, 3, 4, 5 of those. Lab, can't read my writing here. Looks like Lab 7, missing 1, 2 Lab 7s. Test 6, which was the last one we did, missing 1, 2, 3, 4, 5, 6, 7, 8. And lab 8, missing 1, 2, 3, 3 lab 8s, and then we will be doing, okay, I've got a few more labs in now, which is good. Thank you. And of course, the pop test last time, a few people haven't turned that in. And of course, it's too late for that too. Just kidding. Okay. That was for your benefit. Okay. Never mind. Inside joke. Okay. So please, folks, get everything done by next time. Okay. Now, so watch out on email and on Blackboard. Okay? Email and Blackboard and find out when we're going to go on the field trip. I anticipate knowing by, I'll receive an email sometime today. I don't know when I'll get the response for it, but I hope to know by 3:15 tomorrow. Okay? Hopefully I'll know by 3:15 tomorrow. So therefore, if it's going to be Thursday, I won't know any sooner than that. I'll try to get it out there as soon as possible. So it's not going to be a lot of time. If it's next Tuesday, we got the weekend, so we'll get that worked out for them. The trouble is I'm not going to be on campus on Friday to catch up on things, so that's sort of the pain in the neck part of that. All right, I just lost my place in the book. Okay, there I have it. The 10 was in place. Any questions before we get continuing on? Yes?
You agreed to what she said last week about the pop quiz, about me emailing you? Gosh.
I heard about that, Shelby. That was so great.
Like, she's been texting me all week, like, email me.
You gotta text me.
You have to email him now.
Did you
I figured it wasn't 200 points, but...
I found out about it this morning.
Oh, you did.
When you read my email?
Yeah, I saw your email today too, but you didn't give it away in your email. But
yeah, that was funny. That's
yeah.
Shelby texted me on the day he was class, Mr. Fowler had the pop quiz that was worth 200 points. And he had to email Fowler about that.
I figured 200 points was not real. I would have figured 100, but not 200.
Okay.
Yeah,
I can't wait to get that.
All right. Let's move on. All right. Any questions? Any other questions before we get going on continuing in chapter 23? Okay. Where we left off last time, we were talking about the major climate groups. This is along about page 582 in the big text. In the smaller text, it might be off a page or two, but somewhere around there. Okay? I think we hit this slide last time. The primary factors are the intensity of the incoming solar radiation that's determined by the angle of incidence. And every time, I forget to bring my globe in here, but I may go get it in a minute. In the upper latitudes, that angle is always a skewed angle. You know, you're just going off the side. Near the equator, it comes in directly. Okay? This is also, because of the tilt of the Earth, affects the number of daylight hours. The more hours of daylight, the more intensity you get for a longer period. But then on the other hand, the fewer hours of daylight, the further you are in the wintertime, the colder you are. The tilt of the Earth's rotation axis, as I said, determines part of that. The equatorial regions receive more solar radiation because of that direct, the low angle of incidence. The intensity changes on a yearly basis, depending on where you are. Near the equator, it doesn't change a lot. And the number of daylight hours varies annually if you're not near the equator. So these two sub-bullets really shouldn't be under this one. They should be under non-equatorial regions, okay? But I think we already hammered that one out pretty well. This is where we're picking up today. Let's look at the connection between climate and latitude. Okay? Let me go get the globe. I think it's a helpful.
Well, we need black.
there's a 23.5 degree tilt. The globes usually are set up with that. And the sun being somewhere, say Brendan there is going to be our sun today, his radiation is always coming in pretty closely to the tropics, between 23.5 degrees south and 23.5 degrees north, Tropic of Capricorn to Tropic of Cancer, pretty much. These are the low latitudes, the small number latitudes near the equator, high solar radiation, because the angle is very direct, okay? The yearly variation is quite small because no matter what time of year, the sun's almost always directly overhead. The temperatures are uniformly high, with a few exceptions, of course. Tall mountain ranges, for instance, Mount Kilimanjaro in Kenya and Tanzania, is right near the equator. I mean, almost right on the equator, but it has very high elevation, so there used to be always snows on Mount Kilimanjaro. They were glaciers, they're no longer there, but still it's quite cool on very high elevations. So, but other than elevation issues, temperatures are uniformly high. Now, the middle latitudes, that's where we live. This is often called the temperate region. You have higher solar radiation during one part of the year, summertime, and lower radiation during the wintertime, lower during the other part of the year, the months that your tilt is away from the sun. Overall temperatures are lower, generally, but greater variation than the low latitudes. The low latitudes, I think I mentioned this before, I've had friends who lived in Hawaii, and my nephew lived in Hawaii in the Navy for a while, and basically very little variation in temperature year-round. Sometimes you'll have a little bit of variation in rainfall, but most of the time temperature is pretty constant, okay? Whereas here in the middle latitudes, where we live, in the summer we can be quite hot, and in the wintertime quite cold, so our variation is much greater than in the low latitudes. Low latitudes are either uniformly hot or uniformly mild or pleasant, but they don't have a great deal of variation. Now at the high latitudes, this is specifically within the Arctic Circle and the Antarctic Circle, their maximum part of radiation during one part of the year, that's their local summer, and you get maximum radiation. Still very low radiation because even in the summertime, the angle from the sun is very large angle. The incidence from the sun is very large angle, so you don't warm up that much, but you get the maximum amount of radiation during one part of the year, and the other part of the year you get absolutely none. Okay? So you're going to be extraordinarily cold then. See, overall temperatures are the lowest with the widest variation. Okay? Now, why widest variation? Because here in the middle latitudes we can be quite hot in the summer and sometimes quite cold in the winter. That's huge variation. In the high latitudes, cool in the summer and extraordinarily cold in the winter, which is enormous variations. Okay? Even though they don't get as hot in the summertime, you still get so much colder in winter, your variation is extreme. Okay? Now here's the globe that pictures that. The low latitudes are pretty much between the tropics. Tropic of Capricorn, 23.5 degrees south. Tropic of Cancer, 23.5 degrees north. Notice the incident radiation from the sun is almost directly straight in. I mean, perpendicular. So you get the maximum radiation year-round. No matter where you are around the sun, you're always overhead somewhere in the tropics. Okay? In the middle latitudes, between 23.5 degrees north and 66.5 degrees north, or 23.5 degrees south to 66.5 degrees south, those are the middle latitudes. Now we're in the lower part of those middle latitudes, so our incidence isn't bad in the summer. It's a lot less in the winter, but it's never as great as it is in the tropics. The sun is never overhead in the middle latitudes or anywhere other than the tropics. Okay? Brittany's here. There's my phone again. Most of the time I ignore it, but I'm expecting a phone call back. All right, sorry, that still wasn't the phone I was expecting. And what, just one more person has come in, and that's Darius. Got to find you here. Okay, anyone else come in since I called roll? Okay. Whew. All right. So, middle latitudes, the angle is much more slanted, so you don't get as much direct radiation coming in, and you get greater variation. When the Earth is pointed toward the sun, you get maximum radiation. When it's pointed away, you get minimum. So you have wide ranges in variation. And then in the upper, the high latitudes, which are 66.5 north and 66.5 south to 90 in both places, the angle, no matter what time of year, is very slight, so you don't get that much direct radiation. But in half the year, you're getting almost none, and half the year, you're getting the maximum of what you can get, but it's still not very much. But your temperature variations are just incredibly wide-ranging over the year. Okay? Any questions? All right, this develops some what they call climate zones. These climate zones are defined in terms of the yearly temperature averages. So you see these will reflect pretty widely what you see, and this will be the bottom of page, well, actually, mostly page 583 and so. It'll pretty much mirror what we just saw on the globe, and these will be your yearly temperature average. The tropical climate zone are those areas in the tropics. Okay, we called them latitudes before, now we're calling them climate zones. Almost identically the same. Carl's here. Gotta make sure I put you on the right line here. Okay. And let me go and get the slide up here too. And this is again on page, whatever, 383, as I say? 583. Okay? So your tropical, pretty much the tropics like we saw before. Here the lines are not straight lines. Okay? Here, for instance, is the Tropic of Capricorn. Some of these are inside, some are outside. And here's Tropic of Cancer up here. Again, the dotted lines. Some of the line is above and below. It just depends on local variation. But that's the tropical climate zone. Near the equator receives the most solar radiation, generally hot. Okay? Now, not sometimes super hot, like in the Pacific, like Hawaii over here. Pretty moderate, because you got water all around. Okay? But in land area, it's pretty hot. Okay? The polar climate zone, let's go to the other extreme. This would be up above the Arctic Circle or near it. See, here's the Arctic Circle here. Some of this is below, some of it's above. And the southern, just about all of it is above the Antarctic Circle because it's just really, really cold. You got this huge landmass down there which tends to be colder. So just about everything is in the, it makes for the smaller temperate region in the southern hemisphere. Okay, the polar climate zone, least solar radiation, very, very cold all year long. It's just in the winter, it's extremely cold, and in the summer, it's just cold. Okay, constant daylight in part of the summer, constant darkness in part of the winter, contributing to the cold. No solar radiation to warm it at all. And then the temperate zone, that's where we live, and there we are, right there. Okay, we're in the southern part of our temperate zone. It goes up to southern Alaska and mid-Canada, pretty much across the way here, and upper northern Mexico, all in the temperate zone here, as is most of Europe, most of Asia, northern Africa, and very southern South America and southern Australia in the temperate climate zone. Intermediate between the other two, you get more radiation than they do in the polar, but less than they do in the tropics. You get wider range of daylight and darkness hours than you do in the tropics, but not as wide as you do in the polar. Now, intermediate between the two. And then they throw this other in here. Rainfall patterns shift seasonally. Now, somehow to me that doesn't even belong on this slide. It belongs on a later slide. But we see that somewhatly where we live. But there's certain areas of the globe. I know India is this way. I know parts of Africa are this way, probably parts of Asia. They're very much monsoonal. They talk about wet season and dry season rather than summer and winter. Okay? I have a friend who's in Cameroon. He's a missionary there. That's just north of the equator here, north of Congo. And they don't talk about fall, spring, summer, and winter. They talk about rainy season and dry season. So that's why they put it in here. That changes your climate according to that. And like I said, India, I've heard them mention rainy season, dry season, and more parts of Africa. And there's other places that have more of that. We are pretty fortunate that our rainfall kind of goes pretty regular all year. Does anyone know typically our driest month?
August.
Second?
August.
Okay, you would think that. It's usually that's when plants suffer the most. But actually we get more rainfall in August than we do one other month. Say again? No, not July. That's somewhat of August. Actually, it's October. October is typically our driest month, but by then it's cooler and plants are already going to go into their senescence, you know, and so they don't really care as much, okay? But typically October is our driest month, okay? Which is fortunate for us. So we don't have monsoonal things like they have here, but we do have rainfall patterns. Typically, this time of year is quite often some of our wetter times, which is fortunate, but we've had some really dry winters, and that leads to terrible summers, okay? So here's more on the climate zones. This is now the rainfall patterns. And I will promise you something. They're not straight lines like this. This is just the artist's representation of it. Why in the world would there be a big gap like this and a gap like that and a gap like that? That doesn't usually happen, okay? But this is just showing the Western Hemisphere. But basically what they're trying to say is, you see, when it's mostly oceanic, you'll have one pattern that over land might be a different one. Oceanic, land. And this is land, this is oceanic. So that's sort of why the breaks are there, but I promise you, no, they're not sharp like that. They're very gradual, but they do. A later slide will show a little bit better than that. But these are the very wet regions here, again, near the equator, typically. Now, they didn't scoot on over here and show Africa. Africa has some very dry areas near the equator, but generally near the equator is quite wet. Then we have dry north and south of the equator. Notice Mexico and most of Central America. Cuba, they say, but you see, Cuba is an island. They get periodic storms coming in. They can be quite wet. But we are, fortunately, look how lucky we are in the U.S. We have great temperatures. We're subtropical. We're just above the tropics in temperature, and we're above the dry area in rainfall. Yes? Ghana? Yeah.
Yeah, so.
Ghana is right, well, you can't see it here. Let's go back a slide.
But it's in the dry region here, right?
It's what?
It's
Wait, I'm turning the wrong way. Okay, Ghana is right in here, right? Okay. Yeah, oh yeah, you can't see. Right in here.
So I have a question about that because I don't understand why it's in the dry region when
I would say not. It's in the wet region.
it's in the wet region.
Yeah, what you are seeing on this, on the dry, see this is temperature here, tropics here, and most of the tropics are wet, and Ghana would be in that down here, but you see this isn't showing rainfall, this is showing temperatures. This slide here that we were looking at is only showing the Western Hemisphere. Ghana is over here and it's in the wet region.
Oh,
You see, it's over here. This is the coast of Africa. It would be quite wet.
okay.
Is that what you experienced when you were there?
Yes, it was so moist. The air was always moist. It was
Yeah.
kind of hard to breathe sometimes.
Right.
And I thought that they still had like certain, you know how we have, it gets colder and then it gets, I was like, so do you guys, does it snow here? You guys, they started laughing at me like, no.
No, never. Okay. They don't even have any mountains tall enough to have any snow. Yeah. On further east of where you were in Kenya and Tanzania, Mount Kilimanjaro is tall enough they have snow on it, but it's not year-round by any means. It's just occasional. Yeah, you can't see Ghana here. This is where Africa curves around, and Ghana would be right in here, and it would be in that wet region. Yeah. That's only the Western Hemisphere. All right. Now, let's look at some regional climate influences. Not global, regional. 4 major factors, 2 on this slide, 2 on the next one. First is altitude. I've already mentioned that. On the equator, Mount Kilimanjaro can have very cold temperatures, extraordinarily cold temperatures. In fact, there's an old story, I think this is from reality, It may have been made up. But some very strong, rich king, they could look up and see Mount Kilimanjaro. They were down here in the tropics, in the heat and sweltering equatorial area. They could see Mount Kilimanjaro up there, and they saw this bright, glistening snow, the glaciers up there. And the king thought they were diamonds. So he sent his force of men up there to get some of the diamonds and bring down to him. Of course, they went up dressed for the tropics and started climbing the mountain and found out they were freezing to death, before they ever got there. The few that made it to the top, they found out they weren't diamonds at all. It was ice, okay? They chipped off the ice to bring it back down, and of course, before they got back to the tropics, it had all melted. So he had them killed because they stole his diamonds or something. Yeah, I don't know if that's true, but so altitude certainly affects regional climate. Okay, you may be in the tropics, you may be in temperate. If you're in high altitudes, you're still cold. The higher altitude air radiates more energy back into space, especially if you've already got ice on the ground. Okay, because the white ice and snow reflects that radiation right back into the thing. And since there's less atmosphere above you, it can escape just as easily as it came in. So usually the high altitude, very cold, which means mountains. So altitude, mountains. Hey, what's the difference here, folks? Altitude and mountains. Isn't this talking about the same thing? What did we say about Mount Everest?
Well, altitude is like how far above sea level.
Above sea level. So you can be at high altitude without being on a mountain. You can just be at high elevation, but on a plateau or something like that, whereas a mountain is going to rise above your grade. Okay? So again, I was talking more about mountains here. I should have been using that down here. The higher altitude, again, is the air radiates back into space, and certainly on mountains that's even more true. The cooler air at higher altitudes. Now, this is a pretty good statement. Okay? However, in other places it's not stated as well. Remember I said there were prevailing winds. Near the equator equatorial region, the winds typically blow east to west. In the temperate regions, they typically blow west to east. Now, since we live in the temperate region, west to east, that makes a difference, especially where the mountains are. Think about this. There's a ridge of mountains right along the western U.S. There are the Cascades, later the Rockies, the mountains here on the west coast of the U.S. The prevailing winds are coming off the Pacific, typically bringing lots of moisture, right? On top of the ocean for most of that time. But they hit the mountains, and the upwind slopes receive more precipitation because that warm, moist air hits the mountains, the temperature drops, the rain comes down. What do we know about Seattle? It rains and it rains and it rains. One of the wettest cities in the country, not because of temperature, but because the mountains are just inland from them, all that Pacific moisture. Got over the mountains into western Washington state, and you're relatively dry. Spokane, Washington, very dry atmosphere. Not a desert, but still much drier than Seattle. So the upwind slopes receive more precipitation, the downwind slopes less. Now, if you're on the equator, the reverse would be true. The upwind slopes would be coming from the east, and the downwind slopes over here. That's probably why the Sahara Desert is such a big desert. All the rainfall that could be coming in isn't making it there, okay? And then it's sort of in the dead zone here, so it doesn't get a lot of moisture coming in anyway, okay? Other deserts have other reasons, but they're probably somewhat similar. So, yes?
So I never asked this question before.
Okay.
And it might be a dumb question.
Got it.
Okay. So the Sahara Desert is full of sand.
Yeah, lots of sand.
Why is it sand? Like, why is it not dirt?
Okay. Well, sand is dirt.
Yeah, like, you know what I mean? You know?
Yeah.
It's dry.
Okay.
Dry.
It's also pretty windy. Okay. It's also pretty windy, so most of the fine particles that would be your silts and the clays may have blown away already, leaving just the sandy parts.
So if it starts to rain in those areas, it'll turn into like a regular.
It gets a little more regular. In fact, they say in the Pacific Southwest, where we have some deserts, the Mojave Desert and stuff, a lot of the Indian reservations are on those lands. They say when it rains, which is rare, but when it does, just all of a sudden, everything turns green and blooming and stuff like this because they know it's not going to last long, and the plants have a very short opportunity, so they bloom and green up and just look beautiful until they get dry again, and it goes back to being a desert. So it's amazing what nature does with
I was
us.
just thinking that that's where a large body of water used to be or something.
Yeah, and it could be that it once was. In fact, if I'm not mistaken, I've heard that one of the biggest aquifers, which we're going to talk about in the next chapter, is under the Sahara. So they do have water under there, but it's very deep and would be very expensive to pump to the surface. But even if you pumped it to the surface and supported agriculture, you're pumping it out, and if it doesn't have recharge, actually, and this has happened in West Texas, they pumped out so much water with irrigation, and it happens in other places too, that actually the land subsides. Because it was a lot of moisture under there, they pump it all out, and the land actually falls down. Then there's no chance of it ever recharging because the land is where the water used to be. So intense irrigation may sound like a good idea, but quite often it's not as good an idea as we thought. Does anyone know what Mesopotamia is, the Fertile Crescent? Have you ever heard of any of those words?
No.
The Tigris-Euphrates Valley. It was one of the earliest civilizations on the planet. And why it was one of the earliest is because you had these two fantastic rivers flowing in, and it was fairly dry there, but had all this water in the river, so what they did, they got the water out of the river and irrigated crops. And they irrigated the crops. The soil was very rich. They irrigated and they irrigated and they irrigated and they irrigated over centuries. And guess what? That water in the rivers had decent nutrient in it, but it also had quite a bit of salt in it. And if you irrigate with salty water over and over, the plants take the nutrients, they leave the salts behind. Evaporation loses water, but brings the salts to the surface. So after a while, that Fertile Crescent, which supported some of our earliest civilizations known to man, with great agriculture, you have built kingdoms there. What is it now?
Just
A desert. Because nothing will grow.
nothing can grow.
That's what?
That nothing can grow.
Nothing can grow because the soil is way too salty. You know where that is today? Iraq. Exactly. Okay? And that's right in between the Tigris and Euphrates valleys, but they really have a hard time growing anything because over centuries of irrigation, they build up the salt levels so great, it's really hard for them to do. Now, they still have some good agriculture there and stuff, but they really have to leach out the salts out of the water, out of the soil.
It's so interesting.
Yeah.
What about the Dead Sea?
What's that?
The salty, the sea that's extremely salty that nothing can live in it.
Yeah, very little can. No productive crops live there. I mean, certain things that like salty environments, like marshland, stuff like that could. Now, what are we doing in California? We're irrigating with rainwater, and it's the richest, most productive agricultural state in the Union is California. But how long will we be able to sustain that before we salt it up so badly nothing is going to grow, or it's going to be very hard to grow? And we're also dropping the water table, we'll talk about that in the next chapter, And if the land subsides, there's no recharge there either. So sometimes we do some really stupid things. Another rich civilization, early civilization, Egypt, the Nile River. Fantastic, lots and lots and lots of water, okay? And they irrigated, and now Egypt is largely desert, okay? So sometimes...
So we go like kill everything. Keep going.
Yeah, we kind of just destroy ourselves, don't we? We really have some bad practices. I live over, I grew up over in Georgia, and we got farmers around there who are irrigating like crazy. Now, number one, the soils are not very rich in that part of the state. And they're irrigating and not really producing that much crop, but they're pumping the water to it like crazy. Well, when my father dug the first well on the farm, or had it dug, he hit water at 100 to 120 feet. And we used that well for years. Suddenly, well, not suddenly, over time, it just was producing less and less water. So my younger brother's managing the farm now. My dad's dead already. When we built our house over there, not far from where that first well was, we're about 250 feet before we hit water, because all these irrigating farmers help pump the water out. And so far we haven't had any subsidence, but, how long can they go? And they're not producing that great a crop anyway because the soil is pretty bad. But they're pumping the fertilizer to it too. So yeah, sometimes we do some really dumb things. Quite frequently we do dumb things. So 4 major factors of regional climate influences: altitude, how high you are above sea level; mountains, how abrupt you are above the surrounding areas; and large bodies of water. Okay? Now, what difference does that make? I mentioned to you before, and this goes into stuff that was in the first half of the book, which most of you haven't had. Water has the highest, almost the period highest, but one of the highest specific heats of all the substances on the planet, which means it takes more heat to warm up 1 gram of water than it does, say, soil or any other substance. It takes more heat to warm it up 1 degree, Fahrenheit, Celsius, whatever. So water has a very high specific heat. That's what they're saying here. It moderates the temperature changes. Now, I think I've mentioned this before. If you drive down to Gulf Shores in the summertime, quite often you start off pretty hot here in Birmingham, and it gets hotter as you go south toward Montgomery, and it just keeps getting hotter until you get right near the beach, and it seems like the temperature just drops off. Why? Because the Gulf of Mexico moderates your temperature. If you go down there in the wintertime, cold, you might be warming up a little bit, you get on the beach, suddenly you feel like it's almost springtime, because the water moderates the temperature. It's slower heating and slower cooling, so it's more of and that's why Hawaii has almost constant 70 to 80 degree temperatures year round. They're surrounded by the Pacific Ocean. They stay almost a constant temperature. Okay? So large bodies of water produce high specific heat of the water, moderates the temperature changes. A regional climate influence. Ocean currents. They can bring water, we'll talk about this more next chapter, bring water nearby that has very different temperature from the land. And one of the most famous of these, have you all heard of it? The Gulf Stream. The Gulf Stream basically gets water out of the Gulf of Mexico or the region around here in the Caribbean Sea and stuff, really warm water, and it transports it up the east coast of the U.S. And again, we are so stinking lucky, because that Gulf Stream, even up in Maine and New York and Boston and stuff, very seldom do any of those ports ever get icy. Why? Because the Gulf Stream is always bringing warm water up there. They are far enough north they should be frozen over sometime. They're not. But not just them. The Gulf Stream circles on around, and gets over to England and keeps England from freezing over, because the Gulf Stream carries all the way around to there. Okay? Have you ever been to the West Coast on the beach? San Diego, I was in Navy schools down there while I went to the beach a few days. Very beautiful temperatures in San Diego. The water is always cold. And look how much further south it is there. Atlantic City, New Jersey, people go out on the beach in the summertime in bathing suits. In the summertime in San Diego, quite often they wear wetsuits because because the currents go the other way here. They're bringing cold water down. So it's really, really bizarre. Those ocean currents can really change your regional climatic influences. Okay? Let's see what picture they have to go with that. Here it is. Here's the Gulf Stream. The water comes from the equator, the North Equatorial Current, very warm, come into the Caribbean Sea here, into the Gulf of Mexico. The Gulf of Mexico sometimes is like a hot bathtub. I mean, it's just really, really warm all the time, especially in the summertime. And it circles around, and then it makes its way out, and the Gulf Stream goes up here. Poor old Canada. We benefit from the Gulf Stream here, but then there's the Labrador Current, very cold, comes down here and keeps most of Canada's seaports frozen in the wintertime, and ours, because of the Gulf Stream coming up here, stay unfrozen. So we can carry on commerce all the time. Over here at the west coast, we have the California currents coming in here. These are cool currents coming down this way, but warmer currents circling up here. So Vancouver, here Canada wins. Vancouver, Victoria, around in here, very nice, pleasant, even though they're way far north because of those ocean currents. In fact, much of the area of the Yukon and Hawaii and Alaska, the Aleutian Islands, they benefit from North Pacific Current, which is warmer, whereas California, San Diego, stays quite cool, pleasantly cool, the water anyway, because of that current coming from the north. So it's rather bizarre. You have currents that come up the coast of South America here, and we'll talk about this. Well, you'll have a blurb later in this chapter. Off the coast of South America here is the region they have El Nino and La Nina, okay? And that influences our climate way more than you would imagine it would. In fact, a lot of the rest of the world it does. What's happening temperature-wise here has a good impact on what we have here. So ocean currents, and guess what? There was a statement earlier. We know less about the ocean than we do Mars in many respects, because we've sent probes to Mars, we've studied Mars. We hardly know anything about our oceans. We know some things, but comparatively, it's just amazing how little we know. All right, let's move on to describing climate. That was regional climate influences. That was on page 584 and following. Now we're going to be describing climate, 585 in the big book. Kind of tough. There are problems. Like I was pointing out before, there are no sharp boundaries. Okay? Brittany was mentioning the Sahara. The Sahara Desert, there's not a real sharp boundary there. Some areas that used to be pretty lush are now desert again. And some places that may have been desert a short while ago may be getting more rainfall now. There are no sharp boundaries. You can't say it's right there. That's why that map that showed wet here and dry here, that was sort of very artificial. No two places have exactly the same climate. Okay? We talk about San Francisco as having the Mediterranean climate. It's similar, but not the same. Okay? No two places have exactly the same climate. A description of the North America climate zones follows, and this is a very, very busy slide. In fact, well, it's a couple of slides. This is on page 587. So it's a couple pages off from where we just were. But here are the major climate zones. Okay? Now, this sounds a lot like something we talked about earlier. Air masses. Remember, we talked about air masses as being marine or continental. Marine could be marine polar or marine tropical. Continental could be continental tropical or continental polar. Okay? So you have these. Well, here we're seeing the same kind of descriptors of climate zones. We have marine climates. These are the climates near the oceans, influenced by the air masses from the oceans. If those air masses are coming from the north down from the oceans, they may be fairly moist, but not carrying as much moisture as if they're coming from the south. Okay? Continental climates, on the other hand, are far from the oceans, and generally they don't carry much moisture at all. If they're coming from the south, usually very dry, very hot. If they're coming from the north, relatively dry but very, very cold. Okay? Now this year, this winter, we must be dominated by southern climate, air masses. Because, man, we just haven't had much cold weather at all. I can remember 1 week in January and almost nothing in February. It's been what I consider cold. This past weekend, we were over 70 degrees. In early February, 70 degrees, that's unheard of, okay? I was working outside and sweating like crazy because I hadn't we went up to the lake, hadn't taken cool enough clothes. I mean, it was just amazing, okay? So the continental climates far from the oceans, influenced mostly by the air masses from the large land areas. Now, other classifications include things like arid, which means extraordinarily dry, semi-arid, pretty dry, humid, you were talking about in Ghana, very humid, okay? And these are the ones for the U.S. And again, I was saying this is a very, very busy slide, okay? Lots going on. And it's not just the U.S., North America, we'll say. All right. We have some polar regions. These are major climate zones. Northern Alaska, northern Canada, and this dips pretty far south here. All of Greenland, these are polar regions. Even though the Arctic Circle is way up here somewhere, okay? Still we have polar conditions here. This, by the way, does anyone know this big body of water here? Hudson Bay. Enormous body of water. It looks like that's usually very cold water. It keeps the whole area around it very cold. Okay? So those would be the polar. Okay? Humid, continental, goodness, I can't read that. Humid, continental, subarctic. Okay? That would be this region here. Most of Alaska, most of Canada, and out here to the, what is this? Is this Newfoundland up here? I believe so. And these are the, I can't think what they call these islands, but Nova Scotia. Okay. So that's humid, continental, subarctic climate in here. Major climate zone. Poor old Canada, so cold. Okay. Then we have the humid continental. I still can't read that. Humid continental mid-latitudes. Okay? That's this region right here. Okay? Now that goes up into Canada. Okay? This is a little bit of British Columbia maybe. Alberta. What's that next one? Manitoba. In those areas. And right here is the Great Lakes. North of that is Canada, south of it is U.S. Great Lakes. Again, large bodies of water. Notice how they kind of drag this region into here, okay? And that goes across a little bit of this is Canada. That's the St. Lawrence river here coming out of the Great Lakes and stuff. So this is Canada here, but you get down into Maine here, and then the Northeast, New England and stuff like that's here. Upstate New York and Pennsylvania is right over here. So you're in that. So that would be your humid continental mid-latitudes. Then we have the humid continental low latitudes, I think it says. That's what it makes sense. Yeah, low latitudes. Now in my book it's more of a green than a gold, but that's the low latitudes. Now, that's the southern Great Lakes, okay? Some of the Great Plains here. So here we have some of the best farmland. Remember the glacial periods brought a lot of that good topsoil down from Canada, ground it up for us, left fantastic soil in the mid parts of the plains here, and fantastic soil there, decent moisture, okay, decent growing season. They get a little short on the growing season. We live in the humid subtropics. Lots of moisture here. Why do we have lots of moisture? Remember we said most of the moisture coming off the Pacific gets blocked by these mountains here. We should be a desert over here. Why are we not? Thank you, Gulf of Mexico. If it weren't for you, we would probably be far less hospitable place to live. Brianna's here. So we're only missing Coco, Carrie, haven't seen her in a while, and Terry. Carrie and Terry. Okay, but not Brittany Terry. Okay. So, that's where we live, and the reason we're humid, the Gulf of Mexico. Just keeps us pumped full of moisture, keeps us very humid. Of course, it weathers our soils like crazy by chemical and biological weathering, but it keeps us plenty of moisture and plenty good temperatures too. That's why we're humid. Well, we're humid, but we're also subtropical because all this tropical moisture is keeping us warm most of the time. Thank you very much, Gulf of Mexico. Then we have the tropical wet, okay? Now, this is tropical wet. This is the Yucatan Peninsula of Mexico. Nothing in the U.S. is tropical wet. It's just this little bit right here. Not this blue over here. That's what we call marine, okay? It's tropical wet, okay? And then we have tropical with, goodness, I can't read that. Tropical with seasonably wet dry. This is more the monsoon. Tropical with seasonal wet dry, that's down here, okay? Again, not in the U.S., okay? It's in Mexico, it's in the Caribbean, it's in Central America. They have the monsoonal type climates. Wet in the probably late summer, early fall, dry probably from this time on. I'm guessing on those dates there. I've never been there, so I'm guessing on that. Okay, and then we have the semi-arid. That's here, along here. Big portions of the U.S. and much of Mexico, a little bit of Canada, semi-arid. Arizona is even drier than that. That's desert, okay? It's right there, okay? The semi-arid is got enough moisture to sustain stuff, but not excess moisture. And Terry's here. We're slowly filling it up. So now we're only missing Coco and Carrie. Okay. All right. Semi-arid is this pinkish in here. Then we have the desert, that's down here. And there's the Mojave Desert here. Much of this is, now this is the part that I find just absolutely amazing. This is called the Yucatan Peninsula, okay? No, I'm sorry, not Yucatan. The, what is the name of that? Yucatan's over here. is the Gulf of California is right here. Oh, what do they call that? They have, yuck, I'm going blank on the name. But look at this. Pacific Ocean here, Gulf of California here, water on three sides. The only side without water is just very small, and yet it's a desert. It doesn't seem possible. But here's why. Because remember that dead air zone? We have prevailing westerlies coming in here, easterlies down here. This is in between. They're neither getting moisture from the Pacific or from the Gulf of California. What do they call that peninsula? I cannot think of the name of it now, but it's incredible. Desert with water all around it. And then we have the marine up here. This is because of the mountain ranges, catches the moisture off the Pacific, but none of it gets inland. Just past that, and we have the highlands. Those are the mountains that catch the moisture, okay? And they can be anywhere from snowpack to dry, you know, it just depends. These are the Sierra, this is the Cascades here, the Sierra Nevadas here, and the Rockies here. So those are the highlands. And that's what makes the semi-arid right here, because all the moisture got caught there. So you see the gradient? Wet, wet, wet here, dry, dry, dry here. The highlands in between keep the moisture from coming through. Fortunately for us, we have the Gulf of Mexico keeping us moist, keeping us warm, keeping us pretty nice. I like it. Okay, very busy slide, okay? Major climate zones influenced by all the things we were talking about before. Altitude, mountains, nearness to moisture, water, large bodies of water, and continental areas. Okay. Now let's go from regional to local climates, okay? On a small scale. We can get down to microclimates, a local pattern in climate. Now that can be associated with a large city. I think I've mentioned this to you before. I noticed this especially in second mini-term in the fall, okay? That's basically late October, November into December. I teach a second mini-term physical science 112 class, and the guys need that late in the day, unfortunately. Okay, it's the automotive students. They don't start until 4 o'clock or something like that. So I have 4.5 hours after that. So I go to about 8:30. So sometimes it's pretty cold when I leave here. Okay, it's already well past dark. I go out and get in my vehicle. I have a thermometer there. I get out and start driving. And where am I driving? I'm driving north and east. And it's getting later at night all the time. So you would think the temperature would be dropping. Dropping because I'm heading a little bit north. Dropping because I'm heading a little bit east. It's been longer since the sun went down there. Now, not much, I admit, not much. But also, it's getting later in the day. The sun's been down longer. So it should be dropping in temperature all the way home, right? If I leave here in Bessemer, get on 65 or 2059, going northeast, and the temperature for a little while does drop, maybe a degree or two, until I get up maybe near Fairfield or Inslee or somewhere there, and suddenly it stops dropping and starts increasing again. And the closer I get to Birmingham, the warmer it gets. Why? I'm going north, I'm going east, it's getting later at night. Why is the temperature going up? Yes, because of this heat island or heat dome effect. It happens around big cities, large cities. Now, Birmingham isn't that large of a city, but it's larger than Bessemer, you know, and larger than Fairfield and Inslee and those kinds of things. And yes, part of what you said, the buildings and the pavement, they absorb more energy in the daytime. Think of all the dark roads, the asphalt roads, that absorbs heat. And then at night, they release that heat, okay? They emit the solar radiation differently than natural vegetation, okay? Grasses, trees, they're usually moderating. Buildings, think about buildings too. What are buildings doing? But right now at this time of year, you got all the people in the buildings, you got all the activities in the building, all the electricity going on, everything's giving off heat. Cars, the more heat's given off. The more rail lines, the more industry, the more business. Everything is giving off heat. And you got more of that in the cities than you do in the countryside. Okay? So the natural vegetation landscapes always generally will be cooler. These can be, now a microclimate, this is a really poorly designed slide, the microclimate can be associated with a single tree. I don't know any of you woods people, okay? Can you tell your direction just by looking at a tree? How? Yes, the moss, the lichens, those kind of things. In fact, our lake house, my wife was asking me about it. The green, mildewy type stuff is always on the north side because the sun doesn't shine there directly. South side, you never get any of that. So you can look at that in just about anything. The air handling system sitting out there. The north side is green, the other sides are the color of the paint. That's because of that. So a microclimate could be associated with a single tree. Lichens and moss grow on one side, not on the other. And that could be because of the direct sun or not direct sun, moisture or lack of moisture. So lots of things can be associated microclimate-wise. Local climates can get down to very small, what we talked about in the last chapter, landforms. Now let's talk about climate change. Now it's a tough thing to talk about because there's so many opinions on it. And sometimes the opinions are based in fact, and sometimes they're based on opinion only, no fact. Climate change is a departure from what the expected average pattern of climate for a region of time. Now that's a weird statement there. What in the world do we mean by region of time? I think maybe they mean or time. I don't know what they mean there. Time doesn't have regions, okay? But here is the problem. We know that the climate has changed over the history of the globe. Without a doubt. We had at least 4 what they call major ice ages, okay, when it got quite cold and in between it got quite warm, okay? There were times when, and Brittany was just saying the Sahara she thought may have been underneath the water at one time. It could have been, okay? Almost certainly Salt Lake City, the Great Salt Lake, must have been part of the ocean at one time. Well, otherwise, where's all the salt from? But the land raised there and trapped a body of water that didn't drain off. So it remained the Great Salt Lake. Okay? If you think about it, where do we get oil? It comes from dense vegetation, right? And what are the richest oil areas in the planet right now? Saudi Arabia. How much dense vegetation do you see there? Nothing. It's all desert. Okay? But it means at one time that had to be really thickly populated forests and grasslands and things that produce oil. Now it's not. Okay? They're not producing any more oil. They're still pumping out that was produced a few thousand years ago, but they're not making it much new now. Okay? So, sure. Climate has always been changing, okay? Here's the problem, one of the problems, many problems. In recent times, we're collecting data on the climate every day now, okay, or at least a few times a week. So we have very good record of what climate is doing today, and what it did yesterday, and last week, and last month, and last year. But somewhere back there, we don't have much at all. Look at this map. It's going from the year 1000, that would be about 900, from year 900 to 2000, okay? A lot has happened in that time frame, okay? Does anyone know what was happening around the year 10,000, 1000, 1000? Not much. Okay? That would have been basically the Dark Ages in European history, wouldn't it? Yeah, Roman Empire had fallen. Everything was, the only education in Europe was in the monasteries. Okay? They weren't getting education out to any other people. They weren't collecting anything on data, on climate. Yeah. What's that?
I was just scratching.
Oh, you're just scratching your head. I thought you had a question. Okay. So, no one was collecting much data then. So what we have to do is have proxy data. Now, what do we mean by that? Well, we do the best we can.
Like an educated guess?
Say again?
Like an educated guess?
Kind of like an educated guess, exactly. What they could do is drill down into the soil and go through different layers, estimating what time frame those layers are from, measuring the kind of microorganisms or other plant life and animal life that was there, and then we can estimate what the climate must have been like. They do the same thing coring through glaciers or ice flows. South America, Antarctica or around the North Pole, and going through there, seeing what they can gather there. How much carbon dioxide was trapped in the snow. What the level of the carbon was. Was it carbon 14? Was it carbon 12? They can do all sorts of things there and come up with decent estimates of what were happening. Good educated guesses based on the limited data they have, and try to figure out what the past climate was like. If they find buried civilizations, they can study the flora, the fauna, the types of things going on there, and make an estimate of what temperatures it probably was, what rainfall they were probably getting. Okay? So that's why this is what we have there. Just educated guesses here. This is temperature as opposed to time. But what happened around 1400, 1500? 1492, Columbus sailed the ocean blue, right?
Is that when it was like really hot in England? There was a period where it was just like really hot.
Yeah, I'm trying to think when that was. That was probably right between ice ages. Was probably very hot because it went from very cold to very hot to very cold. But there was also a time, I can't remember if it was a volcanic eruption, maybe in Iceland or somewhere, that may have really raised England's temperature. There probably were several things like that. But along about now, we started exploring our planet. So we started getting more data from a wider range, more frequent. So we measured temperatures, at least fairly well, for a while there. 1600, we were fairly well established as colonies by then. 1800, we were already independent by then. 1776 was there. So we have decent data in here, and from 1800 till 2000, we're here. Now, the thing that's the most problematic about this is everything seems to be pretty gradual. Of course, part of this is because we don't know really good data, and this is all averaged out here. But you see things happen sort of slowly until here. Why is a sudden spike here? I mean, it's not sudden, it's over several decades, but it goes up way high. You don't see that kind of spike anywhere else on that measure. Why? What was happening between 1900, early 1900s, late 1800s? What was happening then? Industrial Revolution. You got it. What were we doing then? Say again? Making machines. We were burning fossil fuels like crazy. Before that, they burned mostly wood, charcoal, renewable resources, or they just suffered through the cold, okay? Now all of a sudden we're burning fossil fuels that had taken literally millennia for those fossil fuels to form, and we're burning them up at as rapid a rate as we can dig them out of the ground. The coals, the petroleums, the other things like this, and that's raising temperature. The other thing is, the more we burn of that, the more carbon dioxide in the atmosphere. Now, it's not going up by huge amounts, but a little bit of change of carbon dioxide may make a significant change in temperature. So that may be part of it. In fact, I don't know if any of you saw the, I guess there was a book about it, but also a movie, The Inconvenient Truth. That was back before most of your time. That was done by Al Gore, or he narrated it. It was done by other people. And he plotted some of the graphs of carbon dioxide increases and temperature increases. And man, they almost fall right on top of each other. So there's a good amount of evidence that we are really doing some pretty major things to the environment. This author is not particularly sold on it, I don't think, okay? Many other scientists are just completely convinced there is a direct correlation there. And it really seems like there is, okay? But it can be argued, yes. Uh-huh.
There was an article, a scientist, there are only a few scientists that are saying this right now, but Mars, the ice caps on Mars are also melting. So what they're saying is there's more so of a correlation between the sun, the
Activities.
change,
Yeah.
and anything else that we are doing. Like what we are doing, of course, it
Right.
is contributing, but not as much
Right.
as we think that it is.
Right, and sure enough, I mean, the sun trumps us big time. I mean, there's nothing we can do that will outdo the sun. So and the sun has gone through phases before. They have times when there's lots of sunspots and times when they're not. Lots of times when there's lots of solar flares from the sun and times when there aren't that many. And sure, they are going to have a much bigger impact than something we do. But like you say, we may be contributing to something that maybe here, this was indicating the sun was less active, and suddenly we're, if it's not changing a lot, but if the sun suddenly started being more active, at the same time we were doing this, then we could really have a big problem on our hands. So yeah, all the things work together. More recently than An Inconvenient Truth was one put out Leonardo DiCaprio. It's global cooling right now. Never mind. Okay, y'all awake yet? Okay. He did one, and what was the name of that? He just came out with it this past fall, I think, and it was a National Geographic article that they did on it. Oh man, I can't remember the name. Well worth seeing. See if you can check it out. It's pretty amazing. Okay. So, according to proxy data, Earth has experienced periods of warming and cooling over the past 1,000 years, and before that there were even more, and since that there's going to be more. But these abrupt changes like this, did we contribute to that? Quite possibly, almost definitely, yes. To what extent, that's where everybody argues. Okay. Data about the ice ages and interglacial warming periods, that's what I was saying before, England got quite warm in between the glacial periods, show that periods of warming and cooling occur in large, long cycles. Okay? But, during the past 100 years, the Earth has experienced two warming cycles. Now, this is just 100 years, from 1900 to 2000, so this is a little old this. It warmed here, then cooled a little bit, warmed again. Okay? So that's why they say shows two warming cycles. This gradual one here, and then a more abrupt one there. All that during the, you would say, Industrial Revolution time. It actually started before that too. Temperature changes are not uniform. The temperatures in the southeastern U.S. have cooled since the early 70s. You can't convince me of that too much, okay? Maybe on average, but boy, not recently. The sea ice in Antarctica, in the Antarctic, they say has actually increased. I think when this book was written, that may have been true, but I think since then it started decreasing again. Because I've read and heard people talk about great big chunks of ice falling off the ice shelf there, making their way to sea. So back when the book was written, that may have been true, or when the data was collected way before that, that may have been true, but I'm not certain that's still true today. I know in the Arctic, it's greatly decreasing. Okay. So what would be the causes of the global climate change? And here's the key. Complex interaction of factors. I mean, enormously complex. You can't just say one thing, and Brittany just brought out, or I mentioned, sunspots. What is the sun doing? Solar flares, sunspots. It's doing different things, and that really overpowers anything we're doing here. But if the sun is neutral, then what we're doing could be the thing. And if the sun is doing something that compounds what we're doing, that becomes even worse. Now, the Earth's tilt, orbital shape, axis wobble, all those are going on, right? Always happening, but on a very slow time scale, okay? Now, the greenhouse gases, this is what we're talking about, and water vapor is actually a greenhouse gas, okay? Carbon dioxide, definitely, methane, definitely, and trace gases, to some extent. That kind of stuff is also changing. And now, to me, this is a double or triple whammy here. Tropical deforestation. Okay? This latest thing that Leonardo DiCaprio did, what was the name of that movie?
Called Before the Flood.
Before the Flood, that's it. Thank you. Okay, Before the Flood. He highlights, I know this has been happening in South America, Brazil especially. Okay, Brazil is trying to feed itself. Brazil has no fossil fuels or very little to speak of, so they've been trying to run their economy on soybean oil, basically, natural, renewable oils. So they have been going through and cutting down enormous forests in the Amazon region, in the tropical regions, just cutting them down. They can't use all the wood, so they burn the wood. Okay? Then they plant the crops, and the soils there are very high in humus, because we've had all that tropical rainforest on top of them for all that years. And so they're really good for about 5 to 7 years. They use up all that humus. It all interacts chemically and physically, biologically, and they lose it. And now the soil turns to brick. They can't grow anything there worthwhile. It's just really rotten soil once they've lost all the humus. So what do? Go cut down some more forests. Well, those forests, the tropical rainforests, produce an enormous amount of the oxygen that we depend on breathing. When they cut them down and then burn them, the oxygen is used to burn the wood, and it all changes to carbon dioxide. So there you have greenhouse gases, okay? So it's a terrible ecological practice to burn our rainforest. Yet they're doing it because they're trying to boost their economy. Short term, long term, they may be in deep, deep trouble, okay? We all may be in deep, deep trouble. Over in Indonesia, which is also another tropical region, tropical rainforest there, they cut down the forest there and are raising palm oil, okay? If you notice most of the foods you buy in the store, if you see fat content, look at it, the odds are most of that is not beef tallow or lard or even soybean oil or safflower oil or corn oil. It's palm oil. It's the cheapest oil we can produce rapidly. They're cutting down rainforests so we can produce more of that. Of course, palm oil is one of the unhealthiest oils we can eat, but it's the cheapest, so a lot of our foods are made with it. So we're clogging our arteries at the same time we're destroying rainforests, at the same time we're putting more carbon dioxide in the air, changing the environment. What are we doing, folks? It's crazy, okay?
Just because it's cheaper.
Just because it's cheap. Exactly. Exactly. So, we're doing all this. Can we recover? Okay? Now, unfortunately, this is where the author and I have problems. He mentions here the Intergovernment Panel on Climate Change, IPCC. This is across the world, one of the best examples of intergovernment cooperation that we have. We mentioned the tsunami warnings, that's great. Seismic warnings, that's great. IPCC is another example of across the world, governments have contributed to this. Established by the United Nations in 1988, and here's what they say. Despite research, data, and models, the predictions of the experts vary. Now, especially back when this book was written, which was a while back, and the data collected based on which it was written was even further back, in the probably decade or so since then, more and more people are coming and the variation is decreasing. The predictions of more and more experts are, and the models and the data, they're all coming together and saying, yes, it is happening. All indications are that it's happening. Okay? Here's what our author says. Critical analysis of climate change should be completed before future policies about human-made carbon dioxide are implemented. Now that sounds like a pretty good statement on one hand, right? But guess what? Are we going to have all the answers completely tied up in a nice little bow before it's too late to change it? The odds are not. Okay? If we don't do something now, we may not have the opportunity in another decade or two or half a century or something like that. It may be too far gone. Temperature rises too much, who knows? But he says before future policies are implemented. No, I can't believe that this could even be stated, because if we don't start making some changes now, with all the indicators we've got going, it would be foolish of us not to do something about it. Okay? So that's where he and I have some big, big differences of opinion. All right, that was the last slide. Let me give you the typical end of the chapter pep talk here. Again, the table 23.1 that you saw, the map you saw of the North America that we looked at those climate regions, table 23.1 defines those areas a little bit better. I was thinking that was going to be on the slides. It wasn't. There's also some table here on temperature and precipitation data, okay? And then it's asking you to try to predict, based on these data, which area you might be in, which climate type you're in. And I'll give you a hint. If you've got your books open to that, example 23.3, page 586 or thereabouts, if you look at that, you'll notice most of the months are negative temperatures on degrees Celsius. That means the average temperature was below freezing. It's only June, July, August, and September that were above freezing, and there you only got to like 7 degrees in August, average temperature, whereas February was minus 30.3. You're not in a temperate region, okay? You are in a pretty cold region there. Example 23.4, and they also give precipitation, and notice there, surprisingly, the warmer months are your wettest months. Your precipitation goes up when the temperature goes up. As opposed to what we were guessing, when y'all were guessing before, you were thinking our hottest months were also our driest months. So this certainly is not us, okay? 23.4 shows some more data. In this one, nothing is below freezing. You get down close, like 4.2 degrees in February, but that's still positive. You get up to 26.2 in July. That is really hot, folks. 20 degrees Celsius is, now this is average, is 68 degrees Fahrenheit. So that's normal room temperature. So 26.2 would probably be getting close to 80 degrees, and that's the average temperature, not just daytime temperature, average temperature. That's quite warm. And look at that precipitation. The driest month on example 23.4 is basically almost wetter than the wettest month in 23.3. So this is a very humid situation, very warm temperatures. That would be, they call it humid subtropical. The previous one was, I can't see it here, but I know it's there. So these are well worth taking a look. Okay, cities change the weather. Really good little blurb there. And I was trying to see if maybe that thing in England was mentioned here, but I don't see it. I thought maybe it would be, but it's not. They mentioned the climate change. You've seen most of that. An incredible picture of the ice sheets and glaciers. Sure doesn't look like a sheet to me. That looks like an ice mountain range, but that's the picture in your book on 588. Case study, the proxy data, we mentioned that before. That's well worth a read. The mention of sunspots, you actually see a picture of sunspots there. They appear on the sun's surface as dark spots because they have much cooler temperatures than their surroundings. Now, much cooler than their surroundings would still be awfully hot, but cooler than the other parts of the sun. Sunspots appear in cycles. The latest cycle began to increase from a minimum on January 2008. So we are in a warming cycle according to that. It mentions here the elliptical nature of the Earth's orbit. Also mentions the tilt of the Earth's axis. This is exaggerated big time. And the shape of the Earth's orbit, you know, again, that's the same. Now, table 23.3 is one really good, strong argument for how much human-made contribution to the greenhouse effect. This guy doesn't think there's much, okay? He mentions water vapor. Of course, most of that comes out of the ocean, so we don't contribute a lot there, though we do contribute. Carbon dioxide, 0.1%, okay, not a lot. Total of 0.28%, less than 1%. He says, how is that going to make much of a difference? It doesn't sound like it would, but a little bit of change on one scale could be a more significant change on other scales. People behind the science, Wilhelm Verman Goran Bergerkens, or something like that, okay? A good Norwegian name. He would be a potential paper topic if you're interested. But also, just under that is figure 2336, the carbon dioxide concentration in the atmosphere since 1860. Look at that slope upwards. It's pretty amazing, especially if you go back and compare that to the graph on 2333 that you see a couple pages earlier of the temperature increase in just about that same time period. Okay? It's pretty amazing. And then there's a case study. And folks, if there's nothing else you read from the chapter, read it all from the chapter. But please read this blurb about El Nino. We've just gone through a pretty powerful El Nino. It ended maybe a year, within the last year or so. And that did seem to bring lots of changes. There was a lot more moisture in some areas and other things. In fact, some of this moisture we're getting in California may be a remnant from that. I don't know. Read this. You'll hear Jerry Tracy. Most of the time, he'll mention El Nino at least once. Read this. He'll usually ask you a question about it. So read this. Be ready for that. Worth the effort, the Kyoto Protocol. This guy is talking about that. He doesn't sound overly sold on the idea, by the way. Then there's a summary, okay? And by the way, he places that Kyoto Protocol under mistakes and misunderstanding. I'm not sure that's very nice of him to do that. But anyway, summary I think is a little on the short side, but key terms is probably about normal there. Applying the concepts, there are 45 questions. That's about normal, maybe a little on the low side. 14 questions for thought. That's probably a little below normal. 4 for further analysis. That's about normal. There's something called microclimate experiments. You can look into that if you're interested. And then the parallel exercises, the group A. If you got the big book, you have answers in the back. If you don't, you don't. But those are worth a look too. But especially those multiple choice. Okay? But they have several of those, like I was mentioning before, looking at the climate data and trying to predict where we are in that. Any questions on chapter 23? Okay? So, where are we sitting now? Finished 23. We finished 22 last time, meaning we're going to have, not 22, 20 last time, meaning the test on 20 is the last 30 minutes today. So if you don't have your formula equation sheet ready for 20, start putting those together. We're having that test today. There is no lab today. We already did the lab on 20. The lab for 23 is the trip to the Weather Center. We don't know when that's going to be. I keep listening for the phone to see if they're going to call back. I think they're just going to email now because they haven't called. So hopefully we will know something by Thursday. If I find out that they want us to come Thursday, I will let you know as soon as I know. But that may be as late as tomorrow afternoon after 3:15, because I'm in class from 7:45 in the morning until 3:15 in the afternoon with one 45-minute break. And I'm not sure I'll be able to get all the information I need in that 45 minutes. And I've got to go to the health fair screening then. So I probably won't pick up the stuff until after 3:15. And then I got to go to the Birmingham campus, so it'll probably be 3:45 at the earliest then. So watch for that tomorrow evening or Thursday morning. It may be very short notice. Hopefully he'll say Tuesday of next week. That'll give us a lot more time. Okay. But then too, it's sort of getting into spring type time. Not quite, but it feels like it. We got to take the time when we can, because we could have severe weather any day. And on severe weather days, we can't go because he'll be tied up with that. So, if we don't go, well, let's plan on having the test on chapter 23 the last 30 minutes of Thursday's class. Unless we happen to be at the Weather Center, then we'll have it Tuesday. So, we'll have the test on 20 today. We'll have the test on 23 either Thursday or Tuesday. And then we'll have the final exam on the following Thursday. Unless, of course, that's the day he wants us to come, and then we'll try to work it out and maybe have the test before we go or after we get back or something like that. All right, any questions on chapter 23? If not, let's get out of 23 and go to 24. Last chapter, the one you've been looking forward to, right? Okay. It's hot in here, isn't it? Y'all want the fan on? I'm really, really hot. Okay, let me know if that's too cool or too much or not enough or whatever. I can try to change. All right, here we go. Jackets, here we go. We're still recording, right? Okay. Let's start from the current slide. All right, Earth's waters. I don't know why it jumped 2 slides. But here's the Earth's waters. Not quite the same picture they have in my book, but very similar. There is a nice little caption here in my book. Vast oceans cover more than 70% of the surface of the earth. Fresh water is generally abundant on the land because the supply is replenished from the ocean through hydrologic cycle. One of the first things we'll talk about. But before we go there, let's look at the core concept. And again, in my book, it's white print on a yellow background, which is really hard to read. This is much easier to read. The hydrologic cycle, and that's where we're going to start, and notice how many chapters have dealt with cycles. We have the rock cycle, we have the star life and death of a star. Everything goes through cycles. We did the ice ages, retreating, coming back. Everything goes through cycles, including water. The hydrologic cycle is water evaporating from the ocean, transported in the air masses, precipitating onto the land, and moving back to the ocean and starting all over again. Okay? That's the hydrologic, meaning water cycle.
So is that what they're saying on how we got bathed, like clean water on the land? Is that what they're saying?
Yeah, okay, because the ocean water is salty, okay? Can't support life there. But what evaporates from the ocean is just the water, leaving the salt behind. That's why the oceans are salty, because only the water evaporates, the salts are left. So that when it gets into the air, it's pretty close to pure water. And then when it goes over land, cools off, and precipitates, then you have fresh water coming down. We catch that, and that's where we get the fresh water. But then it moves over the soil, picking up salts, because water dissolves things like crazy, picking up salts and carrying them back to the ocean, and then evaporating again. So, yeah, it's a cycle in every sense, okay?
That must have took a long time for us to get the huge bodies of water that we have this fresh.
You were mentioning Mars. Haven't they discovered, someone was telling me this, the polar regions of Mars have some pretty big ice caps that are pretty much underground. So it seems like a lot of the planets have a fair amount of water. And I think at the planetarium, wasn't he telling us one of the moons of Jupiter or Saturn 1 was just a huge amount of water on it. Enormous reserves of water. So water exists in creation. And we just are very fortunate to have a lot of it, plenty of it, on this little rock where we live. Okay? Thank you very much. Okay? That it's here. Okay. Now, I've seen some really cool illustrations. I don't have any to show you right now, but I've seen them before on things I couldn't capture. Something like a big bucket of water, maybe a drum of water here. Okay? And then a smaller bucket and a little pail, and then maybe a glass of water here, and maybe a spoonful of water there. And they would represent the oceans, the glaciers, rivers, seas, ponds, that kind of stuff, and other water. And really, it's amazing. We're going to get to this a little bit later, how little water we have that's really fit to drink, okay? It's scary. So let's look first at water on Earth, okay? This is 24.1, the first topic here, water on Earth, okay? Goodness, we're getting close to 3 o'clock, aren't we? Okay. All right. Water is the most abundant chemical compound near the Earth's surface. Like we said, over 70% of the surface of the Earth covered with water. Okay? Look at that Pacific Ocean. That looks like close to half of it right there. The Atlantic Ocean, the Indian Ocean, the Antarctic Ocean. Just we're covered with water. The Arctic area, water everywhere. Or any drop to drink, never mind that. Okay. 97% of the water is in the oceans. Okay? The oceans cover 70% of the surface, but they go really, really deep. So 97% of the water is in the oceans. That means it's salt water, seawater, non-potable water. We couldn't drink it if we had to. We could drink it, but it wouldn't do us any good. Okay? Only 3% of the water on the planet is fresh water, that we could drink. But 2/3 of that, meaning 2%, are in the ice caps. Less than 1/3 is available, liquid water. Okay? Pretty amazing. But we've got plenty of it. The hydrologic cycle, as we mentioned in the core concept, starts with the evaporation of the water from the ocean. The water vapor is transported to other locations. Precipitation returns the water either to the ocean. If it rains over the top of the ocean, it just goes right back into the ocean. Or if that rainfall occurs over land, it goes back on the land and then runs back into the ocean. It all winds up back in the ocean again. Now, it may be held on land for a while, but it all winds up back in the ocean. Okay, here is the picture. Now, this actually shows it more than what they show there. The ocean water is 97, they say 97.6, which to me would round to 98% of the water on the planet is in the ocean. Salty water, and you can't drink it. The fresh water, actually less than 3%, 2.4%. That's all, folks. But even in that, 2/3 of that is tied up, locked up in ice. In fact, this is more than 2/3, 78.5%. That's more than 3/4. So the numbers aren't matching here very well. Okay? Now, in sediments underground, these are in 20.6. About 1/5 of the water is there. Now, all the water in the rivers, the streams, the lakes, all this other is less than 1%. So you look out there at Lake Purdy, the Mississippi River, all the rivers and lakes and streams and everything else you see, that fresh water is less than 1%. All of it. Okay. Now, fortunately, underground we got about, yeah.
Okay, I got what you said. So I was wondering, I just got a question kind of off. If you were stranded on an island, how would you get fresh water from the ocean? Like, how could you make that fresh water? Did you, heat it up?
We have to boil the smoke.
Okay, if you had a heat source, you boil it and condense it, and you can drink it then. If you don't have a heat source, you wait for nature to condense it, like catching rainwater and doing like that. Actually, there's some pretty amazing stories. There was a movie that came out a few years ago. Let's see if I can remember its name.
You talking about Castaway?
What's that?
Castaway? Is that what you're talking about?
What?
Castaway?
Castaway, okay. Okay, yeah, that came out several years ago, and that was fiction, but it was probably pretty close to true, okay? Or it could be true, okay? What I was trying to think of, it was a movie about a World War II hero. His name started with a Z. He was a fighter pilot, and his plane was shot down, a bombing pilot, okay, not a fighter pilot, bomber pilot. His plane was shot down, they crashed into the Pacific, and they survived on a raft in the Pacific, at least 2 of them did, for a record number of days. And they did that by catching rainwater, otherwise salt water they could not drink. Does anyone know why you can drink salt water? You sure can, but it doesn't do you any good. Does anyone know why? Because of all the saltiness. Now, why does that matter?
It dehydrates.
Yeah, it dehydrates you by drinking water, because this all has to do with osmotic potential. Okay? Actually, seawater and your blood are not too far apart in constituents. Your blood has iron in it. Seawater doesn't have that much iron in it. But as far as the saltiness, they're almost the same. Okay? So, one of the reasons we drink fresh water is so we can wash the salts out of our system. Those salts are deadly. Okay? We can't, if we don't drink enough water, salts build up in our system and our organs don't function right and we die. We dehydrate, basically. Well, seawater, being the same osmotic potential as our blood, it doesn't flush anything out. In fact, you're adding more stuff to it. And so you do dehydrate. Even though you're drinking water, you've got to have the fresh water for that to work. Okay? And that's why it's absolutely incredible that we have so little fresh water of all the water on the planet. The good news is we got an awful lot of water on the planet, so this is a fair amount of water. Okay. Now, we in the southeast are really lucky. We got the Gulf of Mexico pumping water up to us all the time. Florida is surrounded by water. You would think, and it has more rainfall than probably any other state in the Union. But guess what? Florida, because it has such high population density, they're using fresh water faster than they can clean. Okay? They're rapidly becoming a water deficit state, even though they have more water than any other state in the country. Okay? The southeast, we are really water rich, and yet what's happening right now? Yeah, we're having drought, yes, but more than that, Florida, Georgia, and Alabama are in court just about constantly with each other on water rights, because Georgia's wanting to take more water out of Lake Lanier and the Chattahoochee River and those kinds of things. So they're sending less water down to Florida. Florida says, we got to have that water you're using. You're hogging it all. Not fair, okay? Well, the same, Alabama is in on the same argument. They say, we're taking too much out. And we are some of the richest in water in the planet. Think of the people out west where they've been in worse drought than we could even imagine. And they have huge population densities. Man, we're doing some stupid stuff with water. We're overpopulating is one thing, and we're overpopulating cities and places where we could afford to have more population. People are leaving. Not smart. Yeah. Yes, and moving to the cities, and that is not the best place to be. Okay, water on earth, again, most critical, all this kind of stuff. Oh, did I finish that other? Yeah, I think we did. So here's a picture of the hydrologic cycle. Here are the oceans. There's the waves, you see them. Okay. The water evaporates from the oceans, goes up into the air, forms the clouds, the winds blow the clouds. Some of this goes back into the ocean, rains into the ocean, that goes right back in. The other falls on land. Some of this is absorbed by the land. Hopefully a lot of it is absorbed by the land, but most of it runs off the land and goes back into the ocean. And even that stays in the soil actually evaporates off the soil too. So you have they say there's lots of little sub-cycles in here too, but the big cycle is this one. Now, here are some other dumb things we do. Okay? We go and cut down the trees, kill the vegetation. What is it? They paved paradise and made a parking lot, or something like that. There's an old song that way. We do a lot of things that are really dumb, and more of the rain then goes right back into the ocean. Less of it is absorbed into the soil. We need it to be absorbed in the soil. Why? Let's go back here again. We want the sediments underground. We've only got about a fifth of the fresh water is tied up there. We want more there, but by making more pavement and more things else, more of it runs off and probably gets polluted too. So we're pumping it out, irrigating crops, again reducing this. Not smart moves, by the way. Good temporary, but bad long term. Okay? So you want more of it to soak into the soil, less of it to run off. We're not necessarily doing that. Okay? Now, let's look at our fresh water. Okay? Just to give you an idea where we are in the book, we're now on page 601, or somewhere thereabouts. Precipitation. Now again, precipitation, as from the last chapter, is what falls from the sky. That's what it means, precipitate. To fall out. That's precipitation. It's our basic freshwater source. That's what fills the rivers, fills the lake, before it fills the reservoirs, fills the groundwater. That's where we get it. Okay? Even that's going into the ice, it comes out of precipitation. Now, the fresh water that falls in precipitation, 2/3 goes right back into the atmosphere. Now let's talk about something dumb again. The irrigation. Most of the big irrigation systems, the ones in Burke County, Georgia, where I grew up and still have a little piece of the farm over there. Those people who are pumping the water out of the ground like crazy to raise just a little bit of corn and cotton and stuff, and you know what they use? They use what they call center pivot system, where they spray the water up into the air. And they do this in the heat of summer because that's when the plants need the water, right? So you spray the water up into the air, more than 2/3 of it evaporates right there. They're pumping it out of the ground where it's a reservoir into the thing, spraying it into the air, it evaporates. It doesn't get to the crops. You're not raising any corn or cotton on that. It's going into the air and returning to the atmosphere. Okay? 1/3, the runoff flowing downhill or absorbed into the surface. We want more of it to go into the surface, less of it to flow downhill. That flowing downhill, that erodes. That tears away, takes away topsoil, the very thing we need to grow the crops. And yet we build parking lots. We cover it with asphalt or something else, and then all of it flows downhill, none of it absorbs, or very little. Okay, now this can emerge elsewhere as runoff again, even that it flows into the soil. But it's better to be in the soil than just running off the soil. Now, let's look at this. The runoff groundwater distribution depends on several things. The soil type, I'll talk about that. The dryness of the soil, we'll talk about that. The amount and type of vegetation, big time there. The steepness of the slopes, and the rate of rainfall. All these things determine how much water goes into the soil as opposed to how much runs out. Okay, let's look at the soil type. Name some different soil types we could have. You could have a clay soil. Okay, let's say we have a clay soil. A clay soil is very, very small particle size, therefore very small capillaries in between those particles, meaning that water goes through it very, very slowly. So you have a heavy rain, it hits the clay, it packs down the clay, very little of it penetrates, most of it runs off. Bad news. Most of our soils around here are fairly clayey. Not super, but fairly clayey. So soil type. What's on the other extreme from a clay soil? Sandy soil. Now, sandy soil, large particles, large pore size, water rapidly infiltrates that soil. Okay? But it runs right through it. Okay? It doesn't hold it very well, it just runs right through. So, what we really need is a good mix of sands and clays and silt. And what do we call that good mix of sands, clays, and silt with a fair amount of humus? It's a special type of soil that's named that. Yeah, topsoil is one general name, but the more specific is a loam. L-O-A-M. The optimal kind of soil for retaining water, growing crops. A loam. Good mixture of sand, silts, and clays with a good amount of humus, organic material in it. Okay. Now, how about dryness here? When I was growing up in Georgia, we'd have some hot, hot summer days.
It's 302.
What's that?
That's weird how you said that. It's 302.
Yeah, it's still hot over there. Is that what you're saying? I believe you. Okay.
That is not what I just said.
What did you say? I couldn't hear you.
I said it's 302.
Oh, 302. Okay. All right. You want to take a little break? How about as soon as we finish this slide, we'll take about a 5-minute break. We won't have the test until 4:30, but we'll have a little break before we keep going. Okay? So let's finish this one. Now, what I was going to say is our chicken lot, especially, I used to notice this because I had to do things with the chickens. It would get really, really dry on the chicken lot. And sometimes we take a pan of water that had, say, corn or other scraps and stuff in it, and throw it out for the chickens to eat, you know. The water that was in there actually would beat up on the soil. Because once the soil gets so dry, it's hard for it to absorb moisture. It's easier for a damp soil to absorb moisture than a dry soil. So it's sort of, you would think a dry soil would suck it up like a sponge. Actually, it doesn't. If you have a really dry sponge and pour water over it, most of it runs off. Slowly the sponge will do. But if it's a moist sponge, just a little moist, pour water on it, just like all the water gets held. So actually the amount of dryness, if it's too dry, it actually runs off water easier than absorbs. Okay, now this is a big one. The amount and type of vegetation. If you have a bare hillside, that water is going to run off. The more vegetation you have there, and I'm going to extend that beyond vegetation, the more living or dead vegetation you've got on there, the better it will absorb the moisture. That's why if you have a yard that you're interested in growing things well, mulch, mulch, mulch. Put that dead vegetation around your plants. Now, not all plants will take them, but most of them will, and that keeps the moisture in the soil. It keeps it from evaporating away as fast. Okay? Steepness of slopes. Say again?
Pine straw too.
Pine straw is a type of, yeah, that's what I'm talking about. Actually, now, my wife won't let me do this anymore. She says I'm too old, so she's hiring people to do it, and they don't do as good a job. But I used to, when we get the leaves in the fall, we bought a machine that chops them up, and then I put them in the azalea beds. I did never, the first year we were there, we bagged them and put them on the street. I said, never again. Number one, it's too much work. And number two, we want that vegetation in our beds. We don't want it on the curb being hauled away. So just about everything that we get, all the leaves and everything else, we try to put back on as mulch onto the soil. So pine straw is certainly good. We'll buy pine straw at Home Depot and put around our plants. We'll get wood chips, whatever. The more you can protect that soil, the better. The steepness of the slope, and some of our slopes are pretty steep, so we put plants in there to keep the moisture, the soil in place. Then we put mulch around the plants to keep the soil in place and to hold that moisture, keep it from running off, get it to absorb as much as possible. The rate of rainfall, man, I love a nice slow shower. Has it rained any today? They were calling for rain. It did. Okay, I couldn't tell. This morning was really drizzly. Fantastic. But if you have the really heavy thunderstorms that it just comes out in buckets, most of that's going to run off before it absorbs. And soil just can't take it fast enough. So give me a slow shower any day rather than a sudden downpour. That's the rate of rainfall. Okay, let's see if the picture here. This is showing sort of what they're talking about here. The steeper they have, the more runoff you have. The steeper this way, the more runoff. But if you have places that the soil can absorb it, like more grass, plants, leaf matter, other things there, then the water penetrates here and goes into the groundwater. What we want is to have more in the groundwater, less in the runoff. Period. Okay? And I think that may be a good place to pause. Yeah, we'll start with surface water. Let's take a quick break. This will be on page 602 or thereabouts. Let's take a quick break. No more. I'm glad you caught that. Okay. Come on in. Okay. The Mississippi. And actually, it's more than just the Mississippi. Actually, the Mississippi isn't the longest river in the U.S. The Missouri is actually a little longer, but the Missouri dumps into the Mississippi. So they call this Mississippi, but it's actually the Mississippi-Missouri watershed. The Missouri comes in here around St. Louis and comes from up here and drains all this area. Mississippi drains this area. The Ohio comes in here and drains this area. And basically, the biggest watershed in the continental U.S. is the Mississippi River. I call it the Mississippi-Missouri River watershed, and it drains, it looks like awfully close to half of the continental U.S. And where does it go? Into the Gulf of Mexico. Not into the Atlantic, not into the Pacific. Now, ultimately, it goes into the Atlantic, because the Gulf of Mexico drains into the Atlantic, you might say. But what is it that's right out here? What would you call this? The Continental Divide. Everything east of here flows into the Atlantic. Everything west of there flows into the Pacific. Okay? Now, when I say Atlantic, that could be through the Gulf of Mexico into the Atlantic. But it's into the Atlantic this side, the other flows that side. We have another continental divide here. This is along the Appalachians, and this flows into the Atlantic, this flows into the Gulf. Okay? So that's a minor one. The major one is here. And if you have driven out west, you have crossed the continental divide somewhere there. When we went up to Glacier National Park, which is in southwestern Montana, we went up to, can't think, the something of the sun, the Valley of the Sun, the something of the sun, and crossed the Continental Divide there. This is up high in the mountains, but on one side it flows east, on the other side it flows west. Two of the other major rivers in the U.S., the Columbia River flows through, basically almost makes the boundary between Washington and Oregon, but that's the Columbia River basin. That's the Columbia River watershed flowing that way. Now, some of that's coming down from Canada, others from here. Now, here is another divide. That's not a continental divide, but it divides the water going to Columbia and others south of here. Of course, the Sacramento River goes here. It would have a little watershed. Here's another big one, the Colorado River. Now, can anyone name some major feature that's on the Colorado River? Yes? Say again? Oh, okay. Are you going to another room? Okay. I thought you were going to answer my question. I was so looking forward to that. Okay.
You can I take the rocks test?
Pardon me?
The rocks test.
The what?
The rocks test.
Rocks test?
Yeah, I think that was chapter 18.
Okay. That's this one. Okay, are you going to another room?
Yes, sir.
Okay. Is this one you're talking about, the fifth test? Rocks and minerals?
Yeah, rock.
Let me make sure that's test 4, not test 5, not test 4.
That's right.
Is it? Is that the one?
Mm-hmm.
Yeah, test 5 is the one you have.
Okay. Thank you.
All right. Okay. And someone name a major feature that's on the Colorado River.
The Colorado Rapids.
Okay, I'm sure they're there. Okay. A really major site on the Colorado River. Grand Canyon. Yes. Grand Canyon is on the Colorado River. Right somewhere around in here, I would say. Okay. So, anyway, the Colorado River watershed. Now, this is the Continental Divide here. Here's another divide here. Other rivers feed into the Pacific, like the Sacramento, and I'm sure there's other rivers there, but these are the three big ones. And over here, on the East Coast, Georgia has several. This is the Savannah River here. There's a watershed there. There's the Ocmulgee, the Ogeechee, the several rivers. I know some of the names in North Carolina. I can't think of them now. James River flows down here in Virginia. There's the Hudson River down in New York, between New York and the rest of New England here. There's lots of rivers that dump into the Atlantic. Each of these has a watershed. Nothing compares to the Mississippi, Missouri watershed here. Colorado's big, Columbia big, the others. Rio Grande, of course, has a watershed here that's the boundary between Texas and Mexico. And there's lots of other rivers there. And then, of course, the Chattahoochee flows down between Georgia and Alabama, so it has a watershed. The Tennessee Tombigbee flows in here, I think, in Mobile, so it has a watershed. There's another divide. This is the smaller continental divide here. It goes on up here past for this. Now notice these watersheds go into the Great Lakes, but the Great Lakes flow into the Atlantic. So it's ultimately everything on this side flowing into the Atlantic, everything on that side into the Pacific. Okay. Understood about watersheds and continental and divides. Any divide or continental divide. I think when I drive home going down Western Superhighway, I guess up to Western Superhighway, just somewhere up here, not far from here, you get on top of a hill and you see all of the city of Birmingham. You never see it again until you get into Birmingham. So that has to be a divide there, a ridge there. I bet you Shade's Crest is a divide between two watersheds, okay? So we have divides everywhere. There are major ones and minor ones. This is the major continental divide. Goes on up into Canada and on down into Mexico. Things on the east go into the Atlantic, things on the west to the Pacific. Okay. Now, the ones I'm most interested in is groundwater, okay? Okay? Underground water saturating open spaces between the rock and soil particles, okay? This is water that seeps down through the surface of the soil and goes into what we call those subsurface spaces and fills up the pore space down there. It percolates downward from the surface, 25 times larger supply than all the surface fresh water you have. All the rivers, all the lakes, all the ponds, all the reservoirs, all the streams, creeks, everything else, groundwater, 25 times larger supply. This is what we pump out. If you have a well, you're getting groundwater, okay? Now, often this is within 100 meters of the surface. How much is 100 meters? About a football field down, okay? So most of our fresh water, groundwater, comes within that top, approximately 300 feet, 328 feet, something like that. Most of it is within that range, okay? Not all. In some areas you have to go much deeper than that, but often it's within the top 100 meters of the surface. Okay. Great, important, necessary source of groundwater, of fresh water, is our groundwater, much more than the surface water. Let's see. I don't think this will work. So it's not connected to my computer, so it won't work. Don't see if I could keep from having to walk back and forth in between and blocking people reading. A question or just?
Yeah. My cousin lives in the backwoods, and he says fine groundwater you can use dowsing rods. Is that true?
You do what?
You can use a
Oh!
dowsing?
Yeah.
Yeah, that thing. Does that actually work, or is that?
I have seen no scientific evidence of this, but I know that an awful lot of people believe in it really strongly.
You walk
So,
with it like that?
yeah.
My grandfather did that. And
Yeah.
it turned and it like ripped the hide off of his hands.
Oh my
Because
goodness.
he was like so convinced he wasn't going to let it happen because he was
Right.
so skeptical, and when it turned, it like ripped the hide off.
And what do you call that? Divining rod? Is that what you
Yeah,
call it?
a dowsing rod or binding rod or something. It's like two metal sticks that you like hold in each hand and they cross. You're supposed to be groundwater right where it crosses.
Yeah. Lucky you can get one for oil. No, I'm just kidding. Okay. All right. Did you get it? Okay. So, how does this groundwater flow? Well, the easiest stuff for it to flow through is through sand and gravel. Why sand and gravel? Gravel is large particle size. Sand is pretty good sized particle size. Remember, that's 2 centimeters or greater or less. The big deal about that, because they're large particles, they have large pore sizes. If they have large particles, there's large pores in between the particles. Small particles, very small pores in between the particles. So they're very permeable to water flow. So therefore, sands and gravels will then absorb water really easily. And that absorption is called permeability. Now, I don't quite agree with the lower part of this slide. The top part is absolutely correct. A clay, very small particle size, it says low porosity. Not quite true. It's small pores, but doesn't mean few pores, okay? In fact, there could be zillions of little pores there, but it's very hard for water to move through them. Now, sure, if you take the clay and run over it with 4-wheel drive vehicles and pack it down, yeah, you lose the porosity too. And that's really hard, okay? You can't get anything there. But most normal clay has equivalent to, and sometimes even greater porosity, but the thing is they're small pores where these are big pores. It's easier for water to move through a small pore than through a big pore. Here's my classic example of that. Have you ever gone to McDonald's or one of these places and got one of those big old straws to suck your, say, milkshake or drink or whatever? Pretty easy to drink, right? But you've gone in the morning when they have those tiny little stirring things for your coffee and just have a little bitty hole there. Ever tried to drink a milkshake through that?
Yeah.
You're going to pop your eardrums, okay? Try to suck that through. You can't do it. Why? Because the small pores, you may have a mouthful of those things, but the pores are really small. It's hard to get the liquid through a small pore. It's easier to go through a large pore. So really it's the pore size that matters, not how many pores you have. A clay can have zillion times more pores than a sand or gravel, but they're so tiny it's hard to get the water to go through it. So it's low permeability, not necessarily low porosity. I would say small pore size. That would be the better header there. And it's fairly impermeable when it's saturated or compressed. Now the compressed part, that's when you run over it and you've wiped out all the pores, okay? Yeah, nothing's going to go through that. But not only that, clays tend to be flat, okay? So when you run over them, you mash them down into each other, making the pore sizes even smaller. So to get through that initial layer is almost impossible. Further down, it may be easier to do, but the water can't get through that top layer because they are flat pores and flat plates, and it's hard to get for the water to get around them. So certainly if you compress them, then you lose porosity. And when they're saturated, that means they're filled, but the very tiny pores, hard for the plants to suck water or even gravity to pull water through them. The sand or gravel, the big deal here, large pore size. Large pore size, easier for the water to flow. Okay? Now this is the picture that sort of represents that. And here's the sand or gravel, large particle sizes, but large pore sizes in between them. The clays, on the other hand, very small, but look at this. I mean, in reality, you have as much open space here as you do there, just a lot more of them, but very tiny. So water has a very tortuous route to try to find its way through that, so it's very slow penetrating. So you get a sudden rainfall, most of this is going to run off, a lot of that will make its way through. So it's not that it's low porosity, it's small pore sizes. That's the deal here, okay? Now, they do show these as sort of flat, where these are all sorts of shapes, and if you flatten these out and run over them, like compressing them, then more on the top are going to get flattened in the same direction. So you call that preferential settling. And now it's hard for the water to get through that because it's almost like you got sheets there blocking the water. So that's when you compress them. And then you compress the particles, the pore sizes out of the picture. Okay. Kind of makes sense? Okay. Now let's look at groundwater deposits. Okay. Water makes its way through the top part of the soil. Okay. Water makes its way down. Collected groundwater will form above some impermeable layer. Now here where we live, that's mostly limestone. You go down deep enough, you're going to hit rock. And if you go down deep enough, you're probably going to get a pretty solid sheet of rock. That's your impermeable layer. But the water can pile up on top of that. It may run off some, but it sort of collects it there. Okay? That's called the zone of saturation. Above that impermeable layer where you get groundwater filling almost all the pores, like we saw in the previous slide. Now the water table is the top boundary of that label of saturation. Let's see if we can get a picture here to help. Okay? Not a great picture, but it's an okay picture. Okay, here you have your permeable soil. That could be sand, silts, clays, whatever, that the water runs through. Okay? Somewhere below that, way below it, you have that impermeable layer. This could be your limestone, granite, whatever, that's not going to let much water go through that. So the water sits on top of it. And the water sitting on top of it piles up here, filling all the pore sizes here. Notice this lake dips down into this saturated permeable layer. That's why the lake's there. You may not see anything feeding into the lake. You may not see anything feeding out of the lake, but it's a healthy lake. Why? Because it's sitting into the saturated permeable layer. It's below the water table. In fact, the surface of the lake is the water table. Okay? Now, this looks like this water would drain out, and it will over time, but remember this is pore sizes here, and that delays the water movement. It holds it up for a while, keeping it there, but ultimately it might go into the ocean, maybe underground, that it goes into the ocean. Or it may be in a river flowing into the ocean, okay? Like here, somewhere here, that's going to make its way to the ocean. Quite often near the ocean, you'll have swampy or lowlands, water, let's see, what do they call that?
Marsh.
In marshes, yeah, that's one name for it. There's several names for it of those, lowland water areas. And that could be, they name it here as a swamp. Some people like to drain these, but we won't go into that. But anyway, that would be the somewhat stagnant. Does that mean it's bad? It sounds bad for it to be stagnant water. Actually, here's the word I was trying to think of, wetlands. Wetlands can be one of the best things we have going for us as far as purifying the water that makes its way on down. Otherwise, it could be carrying all sorts of nutrients that we don't need dumped in there. We want them saved, and the swamp will do that for us. It may be filtering out bad stuff. The swamp will do that for us. So wetlands are a very necessary part of your ecosystem. So all this is part of it. But this is what we mean by the groundwater. This water that's underneath the level of the soil, maybe with lakes or rivers or swamps attached to it, they ultimately make their way to the ocean as well. Okay? So the water table is the top boundary of that zone of saturation. Most of the pore spaces here are filled with water. That's why it's called saturated. Okay? The water can move laterally within the zone of saturation, and literally does, ultimately making its way to the ocean. Now, what do we mean by an aquifer? Have you heard that term before? I think I mentioned it when we talked about the Sahara Desert. It contains a fairly large aquifer. State of Florida, right down the center of the state, a fairly large aquifer. Okay? Where's another big one?
I think there's one in Mexico.
In Mexico?
I
I think you're right. Some of the desert areas will actually have aquifers under them. Large quantity of water, people just haven't accessed it yet. Okay? So, it's a subsurface layer of highly permeable material capable, I don't like this term, of producing water. I would say storing water. It doesn't produce water, it stores water, but that means if you tap into it, you can get the water out. That's what they mean by producing. Now, some of these are called artesian aquifers. Those are usually very, very deep aquifers. Okay? Being very deep, they're confined under pressure from water at higher elevations. Now, most of the time, that artesian water is some of the best water you've got going. Remember, quite often, in fact, in Birmingham, we use surface water, Lake Purdy, and some other lakes around. That's where we get our fresh water. You have to clean that, you have to treat it with chemicals, you have to do all sorts of things, because that surface water can be polluted with stuff on the surface. Deer droppings, all sorts of things can get into that water, and you have to clean it up. If this is artesian water, that means it's way, way deep, and that means the earth itself, the soils, the sands, the silts, the clays have filtered that water for hundreds of meters, perhaps. And by the time it gets to the bottom, it is good water. No bacteria to speak of, no contamination, no chemicals, just really good water. Now, if that water is surrounded by limestone, really sweet water. I mean, really good tasting water. That's why most of the water we have here in Alabama, we're underlain by limestone. It's good water. Yeah.
I have a well at my house,
Right.
and you can drink from it.
Yeah.
It's like really irony.
Okay.
What causes it to have all that iron?
Probably it's going, well, I mean, think about this whole area. There's iron ore all over the place. So more than likely that's exactly what's happened. You have somewhere near it, might not be much, it might not be mineable iron, but you have enough iron to contaminate. And the first house we lived in Georgia, we moved there when I was 4 years old, it's water, it's well water. It was real irony too, so I know what you're talking about. On the farm, that really deep, about 300 feet we had to go, 250, 300 feet to go down and get it. Man, that's good water. Okay, my older brother who lives down the road from me, his water always, his well water always gets sand in it. So he has to have traps to trap the sand, and he has to unhook his washing machine every now and then and clean the sand out from the filters and stuff because it's just really sandy. Ours, almost no sand. We haven't detected any, and no rings around the toilet or anywhere else. It is really good, sweet water. Now, the first well that my father drilled on the farm, over where he watered the cattle, man, that was good water too. Maybe a little bit better than ours, the house that we built over there. But then that's the one that went dry when the too many farmers around were sucking out of the water and it was drought and everything else. So my brother, they couldn't use that same place, so they moved less than 50 feet away and drilled down again. That water is not nearly as good as that was, Even though it's much deeper, it had another source. It had a different aquifer. Just happened to be that close together on the surface that was two different ones. The one where we are, really good. Now, my sister's house, she lives on the farm too. She's up on another hill. Hers is sort of irony too, But what's worse, when it rains, it gets all sorts of stuff running into it. So it gets really bad when it rains. Okay. But the artesian aquifer confined under pressure from water at higher elevation. Now what happens then, now this almost looks like this could be, but this is a spring that's just coming basically from the water table somewhere else. I think the next slide, if I'm remembering right, yeah, okay. this is,
I went to get
Welcome
food,
back.
there was a break.
yeah, sorry. Okay. This is another picture. This time we've got really deep water here, an artesian aquifer. This is really, really far down here. Now, somewhere up here, it's closer to the surface, and that may not be artesian water here, but this is where it gets recharged from. But it goes very deep, and the deeper it goes, the more pressure is on it. So then, if this is the water table here, and the picture doesn't look like it would be, but if it is, then this should be all saturated here, but here is your way deep artesian aquifer under all this pressure, way deeper. If you drill a well here, you might have to go very deep to get to it, but then when you get to it, the water comes up to the water table. So you don't have to pump it as far, and that's artesian well. That's what we got at the farm. Now, down the hill from us, and it's not on our property, but it's the next land down and across the road too, so it's not adjacent to us, there is actually what they call an artesian well. And that's what this is, a flowing well or an artesian well. You're actually below the water table, so the pressure on this aquifer, it comes up. Now that is coming from so deep that this stays almost constant temperature all year long, right around 70 degrees. Now one year, trying to think what year that was, I was probably in 8th or 9th grade, it seems like. Okay, thank you. I'm guessing around 8th or 9th grade, our Vietnam was going on at the time, and the Army wasn't really well trained in how to set up field stations, you know, just go into an open field and set up a station. So they started training for this, and Fort Gordon is fairly close to where we live, so they would send people down, and our neighbor leased his farm to them, okay? And his farm was rolling hills, it was cow pastures, he sold his cows or whatever, leased it, making money both ways there. And they set up this temporary station there for a couple of years, okay? And they built a landing strip, and they flew planes in and out to get pilots used to landing on other than perfectly flat runways, you know, like they would have to do in a war zone. That first night, I hardly slept at all, that they started taking off and landing planes all night long. After that, it never bothered me, okay? Learned to sleep right through it. But they had to tank in their water. They had to bring in the water from someplace else until they found out that down the road, less than a couple miles away, there was this artesian well. And once the soldiers found that, they said, let's lease this place to us from a different guy. They leased just a little area there, and they set up their showers there. Because if they had to pull in, you know, bring in all the water, that meant all the water they bathed with and cooked with and drank and did everything else with. They were very stingy with that water. They found out this artesian well was there, and in the summertime, 70-degree water and 90-degree temperature, that felt good. In the wintertime, 40-degree temperature, 70-degree water, that felt pretty good too. They could shower there year-round and have good, clean water to drink. They really liked having that artesian well there, okay? And always good to find those. You don't find them that frequently, but you do. The water is so deep, it's near constant temperature, and usually right around 70 degrees. So let's now look at fresh water. Open and close the book so many times. Open again. This is, and by the way, there's a couple of examples here too, within a watershed, you know, and they talk about things. So I'll let you read that. See, let's see, there's a concept supplied, room for water, the amount of pore space in sandstone, limestone, other rocks. Okay, and another concept supplied, deep wells. After some research, make a drawing to show, and basically what you just saw. Okay, now fresh water is a resource. We've already talked about this earlier. Required for life processes. Okay, fresh water, you gotta have it. All that seawater out there does you absolutely no good if you're thirsty, because that's just gonna make you thirsty. Because it's just raising your osmotic potential, not lowering. Because you're adding salts as well as water. Your body's trying to get rid of salts, the contaminating salts. That's why you drink fresh water, to flush out your system. But not only is fresh water required for life processes, it's required for just about everything we do in a modern industrial society. Let me give you the example of being on a ship. You can't haul all the water you can possibly need. It can't happen. So you make your own water. How do you do that? Well, you have these boilers down there that are providing the steam to propel the ship. So you have a lot of heat going on down there. So they have evaporators that evaporate the water away from the salt, recondense the water. That makes fresh water. Okay? And then you dump the sludge on out into the ocean again. They're always making water. Okay? Not in the old sense, but okay. But they're you're making fresh water. Now, the best, the cleanest fresh water, is that what you got to drink? No. The cleanest, purest water went to the boilers. Because in the boilers, you're heating that water to superheated steam. And if you had any salt particles or other things in it, and you fired that through your propeller, through your turbine, you're going to kill your turbine. So the freshest, cleanest, purest water had to go to the boilers, and that was left over, we got to drink. Sometimes it didn't taste all that good, okay? Most of the time it didn't taste all that good. So quite often, your modern industrial society is requiring cleaner water than we have to drink. So that's where a lot of your fresh water as a resource is going, because anything you're doing with steam, with and that's your making electricity, whatever you're doing with it, that requires really, really pure water. Now, get this. The average U.S. usage is 570 liters per person per day. Now, what is 500? What's a liter of water? Tomato? Okay. This is a little more than half of a liter. So a liter is right at a quart. It's a little bit more than a quart. That's about 3/5 of a liter. Okay? So about a quart. So divide this by 4. That would be 142.5 or something like that. About 150 gallons. About 150 gallons. You use 150 gallons of water a day? Yes, you do. Okay? How do you use it? Well, 40% of that you use, you don't use directly, but it's used to raise the crops that you eat a day. It takes a lot more water to, I'm trying to look for some food here. Oh, you got some food. What you got back there? Rice? Okay, oh boy. To make, let's say, 1 pound of rice. I'm just making a guess here. I would say it would take 10 to 15 to 20 gallons of water to make 1 pound of rice. Because you got to feed the plant, and you get the plant to grow before it ever produces, then finally gets the rice, then stuff. And rice is a really water-intensive crop. I mean, it grows in wetland, okay? So yeah, 40% of that, what did I say, 150 gallons is probably used in agriculture. 40% is used to produce electricity, whether it's hydroelectric water, going over a dam, more likely steam that you use in steam turbines. You heat that with coal, you heat it with petroleum, you heat it with natural gas, you heat it with something, but that water that you use to produce electricity that we use every day, 10% is used for industrial purposes, okay? Like making the plastic you use in that bottle, the the other things, everything industrial that you use, the parts for your smartphones, for your anything you make, that industrial process is going to take. That adds up to what? 40, 10? 90. So 10% you actually use for drinking, for cooking your food, for flushing your toilets, washing your face, bathing. That's that 10%. 10% of 150 gallons, that would be about 15 gallons. Yeah, that would be more what you would think you use, and you do. The other 90% you're also using through the food you eat, the materials you use, the electricity you use, that's where you're using the water. So sure enough, 150 gallons of water per day. Per person, per day. Okay? Most of the supply comes from surface water. Okay? Like I said, City of Birmingham uses mostly Lake Purdy, maybe a few other places. Does Bessemer buy from Birmingham, or does it have its own source? I don't know. I think it buys from Birmingham, but I'm not sure. But the Black Warrior River, people take it out of there, maybe some out of the Cahaba, other places, but most of it is surface water. In surface water, like I said before, you have more sediments you have to filter out, you have bacteria and pollutants you have to screen out, you have to kill, you have to do whatever, you have to get those out of there, and all that depends on precipitation. Did any of you follow Lake Purdy back in the fall?
No.
You didn't. You didn't read in the paper that Lake Purdy was, what did it get down to, maybe 5 or 10% of a full pool? I mean, we were scratching the surface. I mean, we came awful close to some pretty desperate drought conditions. You remember they had us doing that you couldn't water lawns? Yeah. Did you see pictures of it? What was Lake?
Oh, yeah.
A little bitty stream. Okay? So, it depended on precipitation. We didn't get it in the fall at all. And we got awfully close. It's probably pretty close to full pool now. I don't know. We've had pretty good sense. Over 40% of supply comes from, over 40% of our fresh water comes from groundwater, not surface water, groundwater. And that's for all of us who have the wells, and some cities have wells rather than using surface water. And that groundwater is relatively free of bacteria, relatively free of suspended particles, except if it gets iron in it or something like that. However, the energy is used to get it to the surface, because sometimes it's really, really deep. And especially if the city is trying to do on that, it has to pump huge quantities of water. So you have problems there, okay? So probably close to 60% comes from surface water, most of it from surface water, about 40% comes from groundwater. Most of Birmingham area, surface water, because we do have pretty good lakes around here, okay? Now, let's go to the sea. We can't drink this, but what's important about seawater, okay? As we said before, about 70% of the earth is covered with seawater. That's the surface of the earth. The average depth of that is about 3,800 meters. That's 38 football fields. End to end to end, down there. That is deep. That's the average depth. Many places are much deeper than that. A few places, of course, will be more shallow than that. So you're talking about an awfully large quantity of water. 30% of the earth is dry land. If 70% is seawater, 30% is dry land, with the average altitude of 830 meters. Average depth of the oceans? What is that?
That's like
More than 4 times as deep of the ocean as the height of the land. It's a long way down there. And just think about that. 70% of the surface, that kind of depth. What have we explored that much? Hardly anything we know about the oceans. Okay? Most of the ocean is still unexplored. Yeah, we know some of the common places in it, the spectacular places that we have looked at, but there's probably 10 times the spectacular places we've never seen before. And if we knew what was there, we would be flabbergasted. Okay? Most of the ocean is still unexplored. We know most of the land area. Some parts of the land we don't know. Most of the ocean's completely unknown to us. Okay, sorry. Pretty amazing. That's the hidden world all around us, is the ocean. The life that it supports, plant life, animal life, the resources it collects, that's where most of the limestone comes from, things depositing out in seawater. Most of the, I would say a lot of the mineral nutrients deposit out in the oceans, okay? And then later will be uplifted and then we might be able to mine it. It's an incredible, incredible resource we know beans about. Hardly anything. Okay. So, let's look at some of these oceans and seas. How do we differentiate between an ocean and a sea? Basically size, okay? An ocean is a continuous body of salt water covering the Earth's surface, okay? The major ones, the Atlantic Ocean, now they split it in the North and South Atlantic Ocean. It's all one Atlantic Ocean. The Pacific Ocean, they'll say the North Pacific and the South Pacific, okay? The Indian Ocean, there. They usually will say the, well, they don't say it here. Sometimes they'll mention the Antarctic Ocean. It really isn't. It's the south part of the Atlantic, Pacific, or Indian, okay? Those are basically our oceans. Only three, the Atlantic, excuse me, y'all wake up? Okay. So only three major oceans, Atlantic, Pacific, and Indian. Pacific the largest, by far. Look at that, almost half the planet, it looks like, surface area, is the Pacific Ocean. Not quite, but close, okay? Also the deepest. Where is the deepest part of the, anywhere in the oceans?
Right by New Zealand.
The Marianas Trench. Here's the Marianas Islands there. The trench, I think it's on the east side of this island. That's the deepest trench. Deepest part in the ocean. I guarantee you it's way below 3,800. That was average. This is probably way deeper than that. Okay? Atlantic Ocean is second largest. Indian Ocean the smallest. Surface area. Okay? So, those are oceans. What makes a sea? Now, obviously, we're talking about salt water here, so it's not the salinity. The oceans may be a little saltier than most seas, but in general, it's not salinity, it's size. A smaller region distinguished by special characteristics. Now, here are a few of the major seas, okay? The Mediterranean Sea, which basically is the boundary between Europe and Africa. Mediterranean Sea. The Gulf of Mexico, even though we call it a gulf, that's basically a sea. Okay? It's a smaller region than an ocean, but designated, it's got land around most of it. Okay? Mediterranean land around most of it. The Caribbean Seas, that's right next to the Mediterranean. Here's the Caribbean Sea. Now, they just listed a few of these, mostly bounded by land, but not totally. You have the Hudson Bay up here, the Baffin Bay, you have the Bering Sea over here, you have seas all over the place. Sea of Okhotsk or something like that, it's a Russian word. The Sea of Japan, the South China Sea, Bay of Bengal over here near India, Arabian Sea over here. You have seas all over the place, okay? Smaller than an ocean, distinguished by special characteristics, largely bounded by land. Certainly not all the way around, but most of the way around by land. Some of that land may be islands. Okay? I'll hit the button, but those words will stay up. So here are a few of those seas. Sorry if you can't see from there. I can't get over there because it's in the way. But, okay, here's the Sea of Japan up here. I just pointed it out. Here's the Indian Ocean, Pacific Ocean, Atlantic Ocean. Those are. Here's the Mediterranean Sea there. The Black Sea above that. The Caspian Sea and Inland Sea here. The Arctic Sea up here. Okay. The Bering Sea over there, I mentioned that. Gulf of Mexico, they didn't mention. Caribbean here. Ross Sea down here near Antarctica. And this one is Wyndham or something like that. Weddell Sea. That's right off the coast of Antarctica. And Ross Sea, I mentioned that one. So there's seas all over the place, lots of them around. Here was South China Sea, they didn't mention. Sometimes this in here is called the Filipino Sea, and there's tons of them, okay? So there are your seas. Area smaller than ocean, still salt water, but bounded mostly by land. Not totally, but mostly. So let's look at seawater itself, some of the characteristics of it. I mentioned this earlier, salinity. That's why we can't drink it. It has large salt content. Saline means salt. If you go to the hospital and you get saline, that's what they put on. Last Friday, I was having a treatment. Most of what they were putting in me was saline. They mixed the drugs in the saline, but most of what was going in was saline. Salt water. Mass of salts dissolved per kilogram of seawater. Now that's a weird statement, okay? They're trying to define salinity. It's the mass in grams, I believe that's right, mass in grams of salts dissolved in a kilogram of seawater, okay? So basically it's parts per thousand, basically. Because 1 gram is 1,000 1,000 grams make 1 kilogram, so that would be the mass of salts in grams dissolved in kilograms of seawater, so it's basically parts per thousand. It does not change with changes in water temperature, at least not much, okay? Warmer water will dissolve more salts than colder water, but basically the salinity stays pretty close to the same, okay? There are small changes, but not much. Does not change, I would put, does not change much with changes in water temperature. Now, it averages, now this is where I find it really a pain. They say 35% with a 32 to 36% range. That's percents. That's not parts. These are supposed to be parts per thousand, not percents. Okay? And I don't know if they have that wrong in the book or not. Let me see if I can find it. And by the way, I failed to mention this, so let me, while I'm here, mention it. Back when we were dealing with freshwater, there was a closer look on the top of page 606 and 607, or somewhere thereabouts, water quality and wastewater treatment. Okay? Water quality and wastewater treatment. It sort of comes to the same type thing I was talking about being on a ship in the Navy. The purest, cleanest, best water went to the boilers, not to us to drink. Well, guess what? In everything we do, we can get it clean enough for us. May not be clean enough for industrial purposes, but it'll be clean enough for us. Now, this is the part, and this is a little gross maybe sounding, but it's true. Every drop of water in your body has been on the planet probably since the time the planet began. So it's been a part of lots of other bodies, okay? It's been through lots of other bodies, okay? That may sound gross, but it's absolutely certain. I've heard it said before, I can't think of the exact thing, but I bet you every one of us in the room has at least one molecule of water that was in, say, George Washington's body. Okay? It's hard to think of, but the majority of us probably do have. You have to go back far enough. You can't say maybe John F. Kennedy, he lived too recently from now. But, you know, if you go back long enough, then, you know, there's water in your body that came out of a dinosaur in one form or another. You know, there's water in your body that has been through an elephant. You know, yeah, there's water in your body that's been just about everywhere. Water quality, wastewater treatment, ooh. That's what it's talking about, folks. Okay, that probably isn't the best thing to think about. There's some pretty interesting pictures of filtering beds for city water treatment facility. I often wondered, we don't usually have time at the end of this chapter, but if we did, if it would be good to go to a water treatment facility in the Birmingham area. There's one over on 280 before you get to the summit. Isn't that a water treatment area? We just don't have time at the end of a term. That would be interesting to go to, but we don't. If you ever get a chance, see if you can get a tour of a place like that. Groundwater being pumped, there's all sorts of things here. Who uses how much? I can guarantee you this now. We in America are water hogs. I doubt if there's anybody on the planet that uses as much water as we do.
What about China?
They're probably coming close. But if you take the total amount of water they use divided by the number of people per person, they use a lot less than we do. Total as a country, yeah, because they got 3 billion people, 1 billion people or whatever. So yeah, they probably use more as a country than we do, but per person, nowhere close, I don't think. Okay? And they may not use as much as we do, I don't know. So anyway, we talked about oceans and sea, nature of seawater. Okay. What I was trying to find is this. Now, yeah, here's where the error is. This should not be percent. This should be, and the book does it properly. On the slide, they didn't do it properly. They have another, okay. This should be, those should not be percents, they should be per 00. And the text is right. If you look on page 611 or somewhere near that, the average salinity of seawater is about 35 0 per 00. Okay? That means 3.5%. That's 35 with the 00 there, that means 35 grams for every 1,000 grams of seawater. That's parts per 1,000, not parts per 100. A percent means part per 100. This has an extra 0, so that's part per 1,000. So that's what you should be reading, not percent. It's per 1,000. 36 parts per 1,000, 35 parts per 1,000, 32 to 36 parts per 1,000. Not percent. And this thing means part per 1,000. Okay. So, concentration is increased a couple of ways. We said it doesn't depend so much on temperature, and that's true, but it does depend on evaporation. I don't know if that's in the way. Evaporation. When you evaporate water off, the water comes out, the salt stays. So, your base here, 1,000 grams of water, 35 grams of salt, okay? 35 grams of salt is still there, but you just evaporated away maybe 10 or 15 or 20 grams of water, so now you have a larger percent, not percent, parts per 1,000. So the concentration is increased by evaporation, but also by ice formation. Because guess what? Water freezes. Salt doesn't freeze. It gets left out. The water freezes away, and the salt gets left in the water that remains, the liquid water. So it also increases concentration there. So near the equator, where you have lots of evaporation going on, you'll tend to have a little more saline water there, higher amount, parts per thousand. Near the poles, where you have a lot of that water going into ice, then you'll have higher salt concentrations, more parts per thousand there. Okay, and then in between, it all gets mixed around. It's decreased by heavy precipitation. So let's say we had a hurricane form off the coast of Africa, and that moves across and is dumping tons of water, fresh water, back into the ocean. Well, right there, your salinity is going down. When you're out here evaporating water but no water precipitation, the salinity is going up. When the hurricane is coming across, dumping a lot of rainfall into it, your water is decreasing in salinity. Now, also ice melting. So up here, global warming. Okay, if that's happening, where ice is melting down here, you'll have less salinity. Ice melting up here, Greenland, the polar ice cap. In fact, the polar ice cap is hardly an ice cap anymore. Maybe at this time of year it's a pretty solid cap, but in the spring and summer, you can't go over it. You'll go through it, because it used to be you never could break it. Now it's easy to break. Okay, now, the other thing, the proportion of ions are relatively constant. That's what makes the salinity. How many ions are in there? For salt water, it's mostly sodium and chloride ions, but you do have some potassium ions. You have some sulfate ions. You have some magnesium ions. You have all sorts of ions in there. The proportion of ions is relatively constant, but it can go up and down when all these other things are happening. Now, seawater and all water contains dissolved gases. How do you know? How do you know that seawater contains dissolved gases? What's living in that seawater? Plants and animals, fish, and what? Now, whales don't count so much because they breathe the other. Fish, plants, everything, they're having to exchange their gases from the water. So the water must contain dissolved gases. Near the surface, it's higher concentration of nitrogen and oxygen. Why is that? Because in the air, the concentration is about close to 80% nitrogen, close to 20% oxygen. Other gases are mixed in there too, so near the surface you're going to have more nitrogen and oxygen. Deeper, where more animals have been using that oxygen, you get higher carbon dioxide concentration. You don't have all that mixing from the surface, you have higher concentration of carbon dioxide. You get a high enough carbon dioxide, deep enough, and cold enough, and it starts coming out of solution as carbonates, specifically calcium, sometimes magnesium carbonates. That's where your limestones come from. Those large concentrations of CO2 deep in the oceans. That's where most of that is formed. Okay. All right. Here are some of the ions that you do find in the solution. And like I said, the majority are sodium and potassium and chlorine, okay? Sodium chloride salt, okay? That's the dominant one. Now, why is there more chloride than sodium? Well, part of the answer to that is your periodic table. Now, not all of your books have this, but you have the bigger books, you have it. Chlorine is mass 35.45, sodium is 22, or basically 23. Chlorine is 35.5 approximately. So chloride ions are heavier, so therefore their percent by weight would be greater, 55 to 36. But other reason is that other things, you see, now there's one error on this slide, and I can't remember if it's in the book or not. No, it's correct in the book, wrong on the slide. Okay? These ions that are negative are called anions. The ones that are positive are called cations, okay? How I remember that is a T in cat makes a plus, so that's a positive ion, okay? So sodium, magnesium, calcium, this is the error. Potassium, that's a +1, not a -1. Those are all cations, positively charged ions. And notice that, well, it's sort of hard to see for sure. I guess they balance out pretty well. But if you look at the percentage, now this is percentage by weight, not by number of ions. If you did number of ions, these two are almost equal. Sulfate is a very heavy ion because you have all the oxygen in it, so therefore by weight it's really, really big, but the number of ions is fewer. This is all magnesium, that's all sodium, this is all calcium, that's all potassium, so those are concentrated in those, okay? So if you look at it, a lot of the calcium that's in salt water is also calcium chloride. You may have some calcium carbonate down here and calcium sulfate, but not that much. A lot of it's calcium chloride. And a lot of it is, in fact, almost all of potassium is potassium chloride. So you see the chlorides are there not just from the sodium, but from the calcium, potassium, and magnesium probably as well. Okay? So that's one reason chloride is bigger. The other because it's a bigger ion, heavier ion. Sulfate is this high mostly because it has all those oxygen in it. It's not because there's that much of it there. Magnesium, calcium, on down, potassium. Remember, that's a plus, not a minus. The bicarbonate, this is where the carbonate comes from, and calcium carbonate and magnesium carbonate. Now, there's another error. Let's see if they got that right in the book. Yeah, okay. Sorry about this. That minus sign should be up here. All your charges are superscripts. They have it as a subscript. So there's another little error there. And the bromine is a minus as well. Not too much of that, but there's a little bit. But those are most of the ions that you have, the major dissolved materials in seawater. This is an ion. It is time, isn't it? Oh, shucks, just when we're having fun, okay? But we always have fun, okay? So, let's see what the next slide is so I'll know where to begin next time. Oh, let's do this one. It's not much. So, if we have 1,000 grams of salt water, seawater, 35 grams out of those 1,000 is salt. So 650 of those grams are actually pure water. So this is what we mean 35 parts per 1,000. 35 grams of this for every 1,000 grams of seawater. That would be 35 parts per 1,000. That's what that stands for. Not percent like they originally had, but parts per 1,000. Okay. Okay. Oh, yeah. And by the way, if you think back on that previous slide, I don't think that'll mess with any of the words here. Where is this bicarbonate coming from? Carbon dioxide. Some of that comes out of the gas and goes into a carbonate ion, okay, or a bicarbonate ion. So that's where a lot of that is coming from. Some of it could have washed down there as bicarbonate, but it really comes from CO2, dissolved CO2 in water. Okay? Okay. Next time we'll start with the movement of seawater. We talked about nature of seawater. We will begin next time with the movement of seawater. Okay? There's a nice little blurb just above that in the page, and that is estuary pollution. Really a nice little blurb to read. I highly recommend you read that. Okay? We'll talk about movement of seawater beginning next time. that pretty much wraps up all we're going to cover today. The last part, of course, is going to be the test. Everybody got everything you need for the test? You need to take a little break before we get started. Okay? Then let me find the test. It's in here somewhere. Here we go. And all of you ready for test 7. This is the chapter 20 test. Okay? Y'all want to go to a different room? Okay. I think we're going across the hall. For us. There. You ready? All right. Ready? Oh my goodness, I feel like I've run a marathon, though I don't know what that feels like. All right, if no objection, I'll go on and turn off Screencast-O-Matic.